I think somebody started recording. I don't mind, but if you want, like I can also record from my end. So those, I think someone started recorded, right? Maybe you should share with your friends. It doesn't make sense to, everybody records and then, maybe somewhere the same copy of the video is, is there multiple times. I think there are 37 people. So should we start?
Sure, sir.
Okay. Okay. So did you try already experiment number 8 or like any inputs you remember from past, like your lab class? I think I remember we just started, I guess. So but anyways, so right. So in this experiment, right? So basically what we need to do is, I mean, maybe I'll share this PDF. So you're able to see my screen, right? So somebody should volunteer and say yes or no.
Yes, sir.
Yes, sir. Yes, sir.
Okay, anyone, maybe Jayesh, so you can just volunteer for this session. Okay, so maybe you should say
Sure,
yes.
sir, no
No.
problem.
Okay, right, you're able to see the screen, right? Good.
Yeah.
Okay, right, so in this experiment, so basically we need to do the following. So implement a D flip-flop, right? And then, I mean, I presume that I think Anup Thomas sir, or it's a Samir Prakash sir. I think, yeah, it's Samir Prakash sir, right? Your theory course. So maybe here, like I presume that it's like pretty much covered, all the flip-flops, latches, and everything. Okay. So in this experiment, so basically we need to really implement a D flip-flop, and then by using D flip-flop, of course, we need to really implement a T flip-flop. And similarly, so like again using a D flip-flop, and we also need to implement a JK flip-flop. And then the last part, right? So basically, I think we also use that in the next experiment and all. So if you remember, so on basis 3 board, so maybe I'll explain a few things again later. So on the basis 3 board, so we have a onboard clock generator. That means you don't have to give any external clock from maybe, for instance, some kind of a function generator or something like that. It has an inbuilt clock generator. But the problem is that the clock which the basis 3 board generates is 100 megahertz. Okay, so for a naked eye, right? So right, so with like if I mean most of the time if in your full adder or whatever, right? So you're using these LEDs, right, on the which are on the basis 3 board. So if a LED is switching at this 100 megahertz frequency, right, on and off, right? So you won't be able to distinguish between whether it's on or off. It's continuously on, right? So maybe later on when we go for maybe the counter and all those things. So if you operate with this same 100 megahertz clock, and then maybe you wanted to see the count of maybe your counter, okay, on these LEDs. Okay, for instance, we assume a 4-bit, let's say, counter. It can go up from, let's say, maximum 0 to 15. Maybe when all zeros, right? Maybe all the LEDs are off, and when it goes for, let's say, 1111, right? So 4 ones. So maybe all the 4 LEDs are let's say on. But now, if your clock runs at 100 megahertz, you always feel that the LEDs are on, and then you will have an impression that okay, maybe your counter is not working. But in fact, maybe your counter is working, but the problem is that the clock which you are supplying to your counter, right, it's too fast. right? So for that reason, what we need to do is that, maybe as I said, this will be useful for your next experiment. So we need to, you know, kind of convert this 100 megahertz clock to 1 hertz clock. So 1 hertz means, so in a 1 second cycle, right? So you'll get only one pulse, right? So maybe when 100 megahertz means, right? So in 1 second you will get 100 into, maybe this mega means 10 power 6. So many pulses you will get it in 1 second time. The too many pulses mean 1 second, in 1 second time duration, it is switching this 100 into 10 power 6, total 10 power 8 times it's switching. And that kind of, switching activity, with a naked eye we cannot really see it, right? So that is the whole purpose of, converting, this 100 megahertz to 1 hertz. So maybe today we will not see, but of course definitely we will see the code and everything. But maybe in the next experiment, it makes sense to, really, this port this onto the basis 3 and, do your counter thing. Okay. So do you have any questions to my explanation so far? Okay. If no, so I presume it's all clear. So we'll move forward. Okay. So now maybe just again to, just let you know. So why just we wanted to use a D flip flop, right? So why not, let's say T flip flop and a JK flip flop? So there is also a little bit of, kind of a history and all. So if you look at your standard IC design or whatever, right? So generally, like, the fab people, that means the people who make ICs, right? So they give you some kind of a standard cells. That means your basic gates and flip flops and all those things. So generally, they will provide you a kind of a D flip flop. Okay, but maybe in your functionality wise, if you need to realize a kind of a T flip flop, of course, but you do not have a kind of a T flip flop in your standard cells, or the fab guy did not give kind of a T flip flop. What you need to do is you need to realize your T flip flop functionality using your D flip flop itself. Okay, so that is actually the basic reason. And the D flip flop, right, it's a most, used flip flop and most widely available in all the standard cell libraries. Okay, so let's move on. Okay, and then, so in this experiment, right, so what we will be doing is that, right, we will use a kind of a Verilog, of course. So maybe you look at your this 7-4 series of ICs or this MSA circuits, a standard D flip flop is also available for you. Okay, so maybe in your lab in 104, right? So on the breadboard you might have used the standard AND gates, OR gates, NAND gates, and you might have done few experiment. Similarly, a standard D flip flop IC is also available. So I do not know the number yet. I mean, I just forgot the number, but the standard it's available. So what you need to do is just you need to apply a clock and different inputs and test it. But so as part of this course, we also wanted you people to introduce, or we wanted you to learn also a little bit of, basic, kind of a Verilog, so that you also really comfortable with, I mean, in future whether you take any advanced courses or not in this, let's say, specialization. But we just wanted to give a kind of a flavor of, what you can do with Verilog and maybe Vivardo or this FPGA design. Actually, that is the, the intention behind introducing this Verilog. Okay, so now in Verilog, right, so we are just talking about in this slide, so behavioral modeling. So I presume that I have taken one class or maybe 2 hours session for you on introduction to Verilog, right? So if you remember, maybe if you can summarize, if I can summarize my, let's say, lecture. So in Verilog, basically you can express your design in many different ways, right? So we call this a kind of different abstraction levels. Okay, so you can model them at kind of a switch level. That means you can use exactly the transistors or maybe the gates, right? So that's called as structure level description. And then there's something called data flow modeling, where you can use, uh, basically your Boolean expressions. Okay, or maybe you can use what is known as behavioral modeling. So the behavioral modeling is a kind of a highest level of abstraction. That means without going, kind of much details into, how it's going to be implemented. So it looks like a more like a kind of C like language, right? So we can really describe it at a different level. Okay, just to give you an example, so we can have a look. So you're able to see the whiteboard, right, Jayesh?
So it's loading.
Okay,
It takes some time, I guess.
yeah.
Yes, it's visible now.
Okay, right. So I mean, if you look at your, let's say, simple multiplexer, right? So what is a multiplexer, right? It takes, so I'm sorry, like I started using this kind of a small tablet, so I'm also using it for the first time. So in fact, my handwriting is not that bad, but I'm just trying to use this device, so maybe it looks really bad, but so please excuse me. Okay. So basically, you have a select input and a y, but I'm sure that in a few weeks, I will be much more comfortable, right? So what is the equation for your y? So I'm just talking about a 2 by 1 multiplexer, right? So select is your input, and of course I0 and I1 are your inputs. So what is your expression for y? Let's assume that, okay, this is your 0 input, this is your 1 input. So what is the output expression? Hello.
S bar I0, S I1.
Hmm. I mean, please, I want you to speak. Okay. So something like this, right? Thank you, whoever it is. Okay. So now, right, the same thing, as I said, in a very long, so we can use different, let's say, language styles to describe. Okay. So basically, if you look at your code, right, you have something called, module and some kind of a definition you have. So in between, right, so you have some code and you have something called end module. Okay, right, in these two blocks basically we will write code. Okay, so here I'm just writing one way of doing it. So if you look at here, right, so basically if you wanted, you have a s, right? So what you need to do is you need to use, right, of course, an inverter s, and this becomes s bar, right? And then you have this I0. If you wanted to get this first product term, right, so what you need to do is you need to use AND gate, right? Okay, and then what you need to have is I1, and then maybe this, let's say, your I1, and I'm sorry that I'll take this one from here. So you have an AND gate also here. Okay, so sorry, this should be OR gate, right? Because it's OR gate. So basically this is your Y. Okay, so now if I ask you to really implement this gate, right, so you don't have to really think about whether you know Verilog or not, since because you see, right, this is your basically a kind of a OR gate, right? This is your AND gate, and this is also AND gate, and this is your OR gate, right? So then what we need to basically do is, if you know how to describe an AND gate and an OR gate in Verilog, then you are pretty much done, right? So what we can do is, okay, so in Verilog, right? So as I said, like, you don't have to really know much about Verilog. So in a standard Verilog, so you always have a keywords. Okay, so for instance, for AND gate, the keyword is AND. Okay, and then when you are instantiating an AND gate, if you remember, I said like this language is more like a C++, right? So if you wanted to create an object out of your C++ class, right? Of course, you need to mention the class name, right? Something like the module name and an instance name or the object name, right? So similarly, so just I'm writing this and is a keyword. Okay. So this and one is, kind of a instance name. Okay. And what we can do is just we can have this kind of a brackets. Okay. And then, okay. So Verilog language. So this, if you look at this AND gate definition in the language, right? So it has a multi input and a single output. So what does it mean is that, okay, whatever you write the first, let's say letter here, okay, that will be always an output, and then you can have two inputs or three inputs. In this case, let's look at this first, this one, right? This one I'm calling as and one, okay. And now if you look at this gate, right, it has an inputs of I1 and S, right? Okay, maybe I'll just for the time being I will not write the output. So this I1 and then S. Okay, so now if I just write this output as small y0, okay, then I can write as this here y0, right? So now if you have more than, let's say, two inputs, right, you just need to list all those inputs here. So the language automatically takes care of it. So here just we are trying to model kind of a two input AND gate. Of course, as I said, it has only one output. Similarly, now you have this second one, this AND 2 gate, right? So again we need to have this module name, this AND 2. Okay, so if I can name this net as y1, okay, so y1 is output and I0 and S bar are my inputs, right? Of course, in a language, so we need to write this S bar. Okay, I'll tell you. Okay, so here again, so we need to write a y1 and this is your S bar, and then you have this I0. Okay, of course it's something like your C, so we need to have this semicolon, but of course S bar also, right? So we also have a NOT gate. Okay, so not one. Okay, output is my S bar. Okay, input is my S. So basically now you see, right, y0 y1 we have, that is an output of so either like this AND gate or this AND gate, right? So now similarly what we need to have is this OR gate, right? So this OR, of course. So Verilog is, let's say, case sensitive, so we should be really careful. Okay, this is my OR case instance name. Okay, y is my output. Yes, y is your capital Y is your output. Okay, then your y0 and y1 are input. Okay, so now when you're writing this definition, let's say definition of your module, right, you can just write so some kind of this identifier my mux, and within brackets, okay, you can just simply write I0, I1, S and Y, and then here you just write, okay, input I0, okay, and input I1. Of course you can also use this style, S, okay, output, okay, this Y. So this is done. So right, once you know the structure of the circuit, you can simply write it this way. Okay, so I mean this is one style of kind of describing your circuit. So this is called as structural design or a gate level design. But here if you see here, right, I mean you need to really write, there's too much code, like within this block whatever you see, right, this block, so you need to really write so much code. But as I said, so if you know a little bit more, let's say kind of a language, let's say the constructs, right, so we can also describe the same multiplexer using a different a style. Okay, that I'll call it as maybe the data flow model or whatever. Okay, so here I'm just writing only one statement. I can just simply write y equal to, okay, if s equal to 1, right? So have you seen this operator?
Yes, sir.
Okay,
I guess
right?
it's ternary operator, right?
Yeah, right. So if s equal to true, this is a 1 and this 0. So what I'm trying to say that, so instead of this, let's say whole block which you see here, right? Huh? So you can just simply write only this statement, okay, and then it does the same job. Okay, this I call it as a kind of a behavioral modeling. Okay, so this is one style. Okay, so otherwise what we can also do is exactly we can describe the equation. Okay, so for instance maybe I should write something like, there is something called continuous assignment statement. Assign y equals to, right? So s not, right? S, okay, and I0, okay, then plus, okay, s and I1. So this is like exactly describing your equation, right? So this is called as some kind of a data flow model. Okay, and we can also do the kind of switch level, but maybe you need to know about more about MOSFET and all those things. We will not go into the details. So my idea of maybe this, it's the last 5 minutes is that, what I'm trying to tell you is that if you know any circuit, that circuit can be described at different abstraction levels depending upon, I mean, the comfort you have, or maybe the familiarity of you about the language. Okay, but as I said, if you describe in maybe this higher level of abstraction, it's more really independent. But now if you try to describe using maybe this, let's say, gate level, right? You're always already expecting there should be an AND gate, and there should be a kind of a again AND gate and OR gate, right? So what we say that if you grow from gate level to the data flow and the behavior, right? Okay, so the abstraction level increases. But otherwise you can also say that if you come from your behavioral to data flow to gate level, your abstraction, or maybe you are making more depend upon the technology, or maybe how it is going to be implemented. You are just redirecting the tool. So just to summarize, so what I'm trying to say that if you describe any circuit using maybe a lower level of abstractions, so the tools cannot really choose the most optimized way of implementation. But if you describe any circuit using your behavioral, let's say, implementation, tool has a lot of freedom. Okay, for instance if you describe maybe using this level, right? So maybe your standard cell library already has a multiplexer. It just takes a multiplexer, it doesn't even implement it. But maybe you're trying to implement using maybe the structural style, you want exactly this one, right? Though maybe the standard cell library might have a multiplexer, okay, maybe it might go and implement using only this AND gates and all those things, right? That might not be efficient. Okay, so far I'm clear, or do you have any questions?
So I have one question.
Yeah.
Sir, in C, usually code is executed line by line, right?
Yes.
So in this case, you already written used as bar before you defined it. So is this just an example, or in reality, would you have to write the not statement first?
Okay. So it doesn't matter actually. Okay. So
Okay.
here it's the execution doesn't matter. Okay. So I think yours is a valid question. So if you remember, my first class I said that there are some constructs. So maybe the procedural constructs, which are known as always and all those things. Okay. So you can say that multiple always blocks are executing in parallel, but within a always block. So within a always block, okay. So things are kind of maybe you can, for a time being, you can think of as a sequential. Okay, but again there are some concepts like uh, blocking assignment and non-blocking assignments. Okay, so depending upon that, behavior will change. So maybe that is too much for you, but as of now, just to answer you straightforward, it doesn't matter. Okay, is that clear?
Yes, sir.
Okay, good. So we'll move on. So maybe I'll just minimize this one. Okay, so I think just you read this theory about what is described here. Okay, so I think that's what I explained, the behavior, and this non-blocking assignments also, we have seen in the class. Okay, so now coming to the experiment itself. Okay, so what we are trying to do is in this, at least this part of the experiment, so we need to really simulate your D flip-flop. Okay, so basically the D flip-flop is a kind of, of course, data flip-flop or whatever it's called, right? So that flip-flop, as I said, it's a kind of a most versatile, flip-flop, which you can find it in your standard cells. And then we need to really, in this, experiment, we'll try to let's say design and maybe simulate it, and then finally we'll show it on the this basis 3 board. Okay, so now maybe I'll show my VNC. So you're able to see my Linux screen, right? Or
Yes, sir.
okay, good. Right. Just created few things already, so maybe later on I'll share. Okay. Let us. So is my screen visible and the code visible?
Yes, sure.
Okay. Okay. Right. So this is a kind of a Verilog code for D flip flop. Okay. So what do you expect in your D flip flop? Right. Basically, you will have a kind of a D input, right? Okay. And since it's a flip flop, definitely you'll expect a kind of a clock. And sometimes we have a flip flop without reset also, and we have a flip flop with reset. Okay. Maybe I'll ask you one question here. So what is the use of reset?
So it is an asynchronous kind of input. So if you give, if it's an active low reset, if you give the input as 0, it will reset the output to 0. Like it does not matter what the other inputs are. It's basically an asynchronous input.
Okay. So now is Vaibhav right?
Yes, sir.
Okay. Good. Good. Thank you. So now, the questions, like following questions are for everyone. Okay. So Vaibhav said asynchronous input, right? Why do you think that the reset should be only asynchronous? So why cannot be it synchronous? So now then you should know what is the difference between asynchronous reset and a synchronous reset. Okay.
Uh,
Maybe Vaibhav, like we will come to that later. So maybe this I will ask you part of this report submission, right? So I'll ask these few questions there, so everybody can answer there. Okay. So
okay.
now, so just to correct or whatever. So reset can be asynchronous as well as be synchronous. Okay. Only the difference is that when it asynchronous means whenever that signal is active, right? So it will be respected irrespective of the clock edge you are interested. That means when we say it's a synchronous operation, right? So synchronous means everything happens with respect to a clock edge. Either it could be a positive clock edge or the negative, clock edge, right? When you say it's synchronous, everything is happening according to a kind of a determined, or let's say pre-agreed, clock edge. Either it could be positive edge clock or a negative edge clock. But when it's asynchronous input, it doesn't really care for kind of edge. Whenever the signal is active, so then your output will be either set or reset. Okay, here generally most of the flip flops we have a reset. That means you wanted to set the output to maybe 0. Okay, so that we call it it's a clear or a reset input. So this could be synchronous or asynchronous. And then most of the time also we also have another input called preset. That means it will again a kind of it could be again a synchronous or asynchronous, and then it will set your output to already to one preset and a clear. And this preset and clear is like whenever we have a preset, so we will use clear. But in most of the time we don't have a preset, and then we always use what is known as a reset. Okay, so I mean in general in a sequential circuit the reset is used if something happens we do not know which state we are, right? Okay, so what we'll do is, so we try to press this reset so that we will start from a kind of a fresh state. I mean that is actually happening in your mobile phones or your routers and all. If nothing works, what they will say that, okay, so maybe especially on your router, so there is a small hole on the back side, they will ask you to take a needle or some kind of sharp object and then try to press for maybe 20 seconds. Okay, so basically what is happening is that, okay, so when you press that in a small button, some kind of signal is generated. So maybe it needs really 20 seconds or whatever to really clear the state of the machine, and then when you release it, it will again start from a known state. Okay, so that is generally the idea of reset. If something goes wrong, you do not know where you are, so just reset it, and then you always start from a known state. Okay, good. So now coming to this, let's again D flip flop. So as I said, this module and end module are the keywords. It's like a kind of a class definition, right? So like a module and this end module, and then whatever the logic you need to describe, you need to describe within these two statements. And then the module, then identifier, it could be anything. So I just choose it to be DFF, and then within brackets. So you can just, there are like different styles of describing these names. Okay, but this is very simplistic. So you can have just signal names defined. You don't really mention whether it's an input or an output here. You just declare what are the kind of signals here. So Q, right? Of course, D flip flop has a Q, and then you have a Q bar, right? Okay, so the Q bar, and then these are like basically two outputs, and then this is your D, right? So this is D input, and the clock is an input, and RST is an input. So basically, you can expect that it's a flip flop with total 3 inputs, D inputs, clock, and a reset, and the 2 outputs Q and Q bar. Is that clear so far?
Yes, sir.
Okay, right. So then let's come to this section. Okay, so here in this section, so since we are not declaring which is an input and output, right? Of course, any language or any even CRLs, right? So we need to really define these variables, what kind of variables they are, and whether it's input and output, right? So if you look at this input, right? Let's start from here. So we are saying that input, I mean D, clock, reset are inputs. Okay, so that's what I did here. So I mean you can have let's say one signal defined on each line, like input D semicolon, again next line input CLK semicolon input RST, but you can also define them everything on the same line, doesn't matter, like I did here. Okay, so by default when you say it's an input, okay, so in Verilla language, if you remember my first class, there are like two main data types, a wire and a register. Okay, so wire and a register. Okay, so the other data type is a register. Okay, so here this Q and Q bar, right? Okay, so of course basically they are output, and then this reg Q, and then output reg Q bar. Okay, that's why we defined. Again I just followed the other convention. Otherwise I can also have here reg Q comma, right, reg Q bar, but it's up to you how you wanted to write it, so feel free. Okay, so now as I said, like these inputs are by default, if you do not write any kind of a qualifier here, they are just simply wires. Okay, But now if you look at this output, right, the data type is a reg. Okay, so if you again remember, let's say my class on Verilog, so I explained at least one difference. So do not I mean, at least this I made this statement, do not confuse the Verilog kind of a register, let's say kind of a data type, with your digital logic register. In a digital logic, or maybe in a digital design, whenever you are saying a register, maybe you are trying to refer to a flip flop which can store 1 bit. I repeat, so in your digital design, when you are referring to a register, you are always referring to a kind of a flip flop which can store a 1 bit of information. But okay, in Verilog, this reg data type, it's just a data type. It might result in a kind of a register which is equivalent to a flip flop in your digital design, but sometimes it might not result in a register which is equivalent to a flip flop. I repeat what I said. Okay, so what I'm trying to say that in Verilog we have this register variable. When you implement this Verilog design, for instance, Q and Q bar might result in a kind of a flip flop which is equivalent to a register in your digital design. But it's not necessarily that whenever you have this register variable, when you implement your circuit, okay, it should result in a flip flop. Is my statement clear?
Yes, sir.
I think somebody voice was a bit not clear. You have a question? Prabhat? Okay. So I'll come back to this later, maybe if somebody has a doubt. So the only point which I'm trying to make is that, okay, again, if you look at this, what I said, this always blocks are a kind of a procedural statements. So the idea is that the language expects that whenever you have this always block, all these left hand side variables, Q and Q bar, they should be kind of of register type. This of a register type. Of course, as I said, when you declare this as a register, it might result in a flip flop. It might. It not necessarily that it should result in a flip flop. Okay. But in this case, I mean, when you implement, it will result in a kind of a flip flop. Okay. But it's not necessarily. That's what I wanted to let's point out. This register is a kind of a Verilog register type, and it's do not confuse that with your digital design a register which is equivalent to flip flop. Hope I'm clear. So we'll move on. Okay. So now in this block, what is written is you're actually the kind of a functionality of your D flip flop using your behavioral code. Okay. So now, I mean, in general, so you can think of this always, right? So what is the English meaning of always, right? I mean, it has always executes, right? So that is actually the meaning of it actually, of course, in fact. So that means this block, whatever you write within this always block, which is starting from here, the begin and the end, right? This block will be executed whenever something happens which is mentioned in this brackets. This we call, whatever we write this in within this bracket, we call it as sensitivity list. Okay, this is a posage of CLK. Okay, that means, so whatever you wrote in this block, that should start executing whenever this posage of the clock is coming, right? I hope you understand what is the posage of the clock, right? Okay, so now whenever the posage of the clock is coming, so please execute this code. Okay, what is this code? Let's have a look. As I said, it looks like an if else block, right? So it's like a much more looks like your C. Okay, so what we are saying is that if not reset, That means if reset equal to 0, not reset will become 1. That means reset equal to 0, not reset will become 1. This is a kind of a negation, a logical negation. So RST, right? So RST equal to, if reset equal to 1, this negation will be 0. That means this block will not be executed. But if RST equal to 0, let's say logical negation of your RST, right? It will become 1. This block will be executed, right? Okay, assume that let's say reset equal to 0, then this block is true. This should be executed. Again, any if and right else blocks, they should also have a begin and end. If you have more than one statement, if you have only one statement, it doesn't matter. You can just let's say omit begin and end. But anyway, it's good practice to have all this begin and end. So now we are saying that if reset equal to 0, this block gets executed, and then we are saying that the q should be assigned 0 and the q bar is assigned a 1. Okay, and now if you look at this one, right? So these are what is known as kind of non-blocking assignments. Okay, again I'll come to this later. Okay, just for the time being we'll just follow the code. Okay, so now in case if the reset is not active, that means reset equal to 0, right? Of course this block is getting executed. If reset equal to 1, right? 1 means this logical negation is a 0. This will not be executed. This block will be executed, right? When this block is executed, what we need to do is, okay, so we need to assign this D input, right? Whatever the D value of this input, right, should be assigned to Q, and of course your Q bar, right, it is just a complement of your D. And then if you look at your D flip flop, right, your output equation is nothing but D, right? Q equal to D, Qt plus 1 equal to D, right? Next state equal to your just input itself. So what, right? That's the reason we call it as data, a flip flop. The output follows the input. Am I clear?
Yes, sir.
Okay, so we'll move on. So I presume that like there are no questions in this one. Okay, so here what I need to explain is only what is the difference between what is meant by this non-blocking statement. I'll come back. So for the time being, you just treat it as a normal assignment, but of course it's not much more than that. But for the time being, you assume it as normal assignment. Okay, we're done. Okay, right. So now, so since we wrote this code, right, I presume that we are okay with it and we understood. So then what we need to do is we need to really write some kind of a test bench, right? Okay. So here and let me make it a little bit big so that you can see. So you're able to see the code, right?
Yes, sir.
Okay. So now if you see here, again the test bench is also kind of a Verilog module. Okay, but it doesn't have any inputs and outputs, right? So of course, so what I'm trying to do is that, okay, I just wanted to so have my, let's say this is my, it's a D flip flop. Okay, it has this clock input and this is my D input and this is my Q. So I think I use small letters, so let's stick to that convention, this Q bar. So now if I wanted to simulate this block, what I need to do is I need to instantiate this in a kind of a bigger block. Okay, this I'm calling as, I think, test bench D flip flop. Okay, but of course this test bench D flip flop, right, it doesn't have any inputs or outputs. That means it doesn't communicate to the external world, but what it does is that it will try to supply some kind of a stimuli. That means input to this one. I think in the code I called as a capital D. I think this was small d. Okay, and then it will try to supply a kind of a clock I'll try to generate a clock in the within the test bench, and then I'll try to give it, and then I'll watch. Maybe I will print out this Q and Q bar, right? So I just call as a capital Q and capital Q bar, I guess. I will watch this Q and Q bar. So what I'm trying to do is that in my this module test bench D flip flop, again it's kind of a Verilog module. So I'm going to instantiate this D flip flop, okay, and then generate this D input and this clock input, and then I'm going to observe the Q and Q bar, these two outputs. So what is the kind of a, I mean, if I change anything with let's say D with respect to the clock, so I wanted to see what there will be the change in Q and Q bar, right? So that's what I have here. As I said, these are really internal to the clock, internal to the module itself. Okay, your register D, CLK, RST. Okay. So then again I said this wire Q and Q bar. Okay. So here if you look at what we did was we are trying to instantiate the D flip flop inside your this TB DFF. Suppose in your C++ also you wanted to instantiate object of another class, right? You can do it. Right? That's what I'm trying to do is, right? So this DFF is kind of object of another module or instance of another module. So what I need to do is I need to write that module name. We know that the module name was DFF, right? And this is my instance name DUT. Okay, and then I need to make the connections for the D flip flop, right? So I know that the D flip flop has a Q output, Q bar output, and a D input, and a clock input, and RST input. So here, this is called as a kind of a named connections. Okay, I mean there's also another way where you can just list the order as exactly uh, which is defined in your let's say module. Maybe I'll explain that later in a minute. So here what you're saying that there is an input called Q. That Q input, sorry, output should be connected to the Q of this wire. Okay, and then there's also output called Q bar. It should be connected to Q bar, and then there's an input called D that should be connected to the D input here, and there's a clock input that should be connected to your clock signal. So RST input it should be connected to RST. So again if you look at, so what I'm trying to say that this small D input is connected to D, CLK is connected to this capital CLK, Q is connected to Q and Q bar, and of course I forgot a reset. There's a reset pin here, it's connected to RST. So here my idea is that all these D, CLK reset I need to generate within a test bench, and then I should be able to observe the output. Okay, now if you look at, there's a dot here. Okay, I mean this is according to the language kind of a syntax. We always need to write a dot against any input or output. Okay, so now other one which I was trying to tell you is that, so we know, I mean this construct is also really valid. So exactly the order of your let's say signals, right? In your input or maybe in your module, let's say D flip flop definition, that you defined in the beginning Q, and the second signal is Q bar, and the third signal is D, and the fourth signal is CLK, and the fifth signal is RST. Now you don't have to really let's write this dot Q and all those things. What we can also do is simply write Q bar, CLK. Sorry, I think we should write it D. Sorry, D of course, and then CLK. And no, what I'm trying to say that these two statements are, I mean, equivalent. So here what will happen is that this Q will go and connect it to exactly the Q, because in your module definition, the first signal was, the first input was, the first signal which you encounter was Q, and then Q bar will go and connect it to Q bar. So again if you wanted to really recollect, so we can just look at your D flip flop definition, right? If you see here, the first signal is Q, second signal is Q bar, D, CLK, RST. Okay, RST, right? So here either you can follow this approach or this approach. just it follows the order of the order which is defined in your original definition. So this q will be going connected to q bar. But the problem is here you need to really remember, I mean, which was the first signal and the second and the third. But if you have this kind of approach, I mean, you don't have to really worry about, you can change even the order. But instead of here, if you have something like this q bar and a q, then everything is wrong. So q bar will be connected to q and q will be connected to, you know, q bar, right? So that is the reason like this kind of a style is bit discouraged, but without, I mean, with proper, you know, kind of a care, that also can be used. So am I clear?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
Okay. So here again, you know, this test bench also we need to define some signals first here, like you do everywhere, and then this is instantiation, and then this comes there, like as I said, there are two procedural blocks in your Verilog. One is, you know, initial and another is always. You can have multiple, let's say, initial blocks and multiple always block. Okay, so whenever you have an initial, this initial block is executed only once. Okay, now your simulation started at time 0. From time 0 it will start and then it will execute further, that's all. But if you have this always blocks, whatever you write in this always block, so that will be, you know, keep on executing multiple times depending upon what you write here. But in this case I'm not really writing anything, that means, you know, it will execute always. Now it will not wait for some event to occur. Okay, now if you see here, there is also some initial block here, right? So now as I said, this initial block also we can have, that means multiple initial blocks we can also have, multiple always blocks we can have. But even the difference is that initial blocks will be executed only once and the always blocks will be executed multiple times depending upon what you write, you know, in your sensitivity list. Okay, so here, so maybe, you know, with this, you know, example it will be clear. Okay, so here what I'm trying to do is that, I mean, especially with this, you know, inputs, right? So here, I mean, inputs only we can change, right? Outputs we cannot change. Outputs are your functions of inputs, right? So you wanted to really control the inputs in the beginning. Okay, so you're trying to really apply first for the this D signal at D equal to 0, and let's say clock equal to 0 and RST equal to 0. So that means at the very beginning of your simulation, you're trying to make sure that D equal to 0, clock equal to 0, RST equal to 0. Okay, now let's look at this block. We are saying this hash stands for some kind of a delay after 100 time units. I mean, it could be seconds or nanoseconds, doesn't matter as of now. We are saying after 100 time units, clock equal to not clock. So what does it mean? If it is 0, it should become 1, and if it is 1, it should become 0. So now let me go to the whiteboard again. So here let's assume that this is your time 0. Okay, right? So you are saying the clock equal to 0, right? Let's say this is your 0 and maybe this is your 1, and let's say this is your time equal to 0. Okay, now if you assume that this is your time is 100 units, so what we said, that always block, right, it should be executed every time. So when you reach this 100 time units, it should become clock equal to not clock, right? Earlier it was 0, then it should become 1. Okay, now it's again 1. And now again it's waiting for 100 units of delay. Again, if this is 100, let's assume that this is again, I mean, incrementally 100, or the final value is 200. Again, now we are saying clock equal to not clock. That means it will be something like this, right? Again, it will continue after again 100 time units or 300, it will become clock equal to not clock. So basically what you are trying to do here, Vaibhav?
We are trying to generate basically the clock signal.
Okay, good. Right, so that's what you are trying to do here, right? So maybe in a basis 3 board, maybe on board some clock is there, we will try to use it. But in a test bench, right, it's in the everything in the software, right? So somebody need to generate this clock. So that's what I'm trying to do here. Is that clear? Okay. right? So now we'll go back here. I mean, that is the intention, that clock equal to 0 and clock equal not clock. Of course, you can ask me, sir, why in the beginning it's 0? Of course, you can start with 1, then it will the situation will be little bit changed to, in the beginning it will be 1 and then it will be 0. It doesn't matter. It's up to you. Okay, good. Right? Here, I think this is clear. So now let's look at this block. Okay, the main the point is actually very, one of the important thing is just to understand this one. The rest everything is very simple. Okay, here as I said, any initial block, right, it start from time 0. So now here if you see, let's say before d there is no time unit like this hash 100 or hash or anything. That means by default it's a 0. If you do not keep like specify anything, it's a I mean it's a time is 0. So at the beginning it is d equal to 0, right, and of course clock equal to 0 and rst equal to 0. But now if you look at here what we're trying to do, okay, in this initial block, okay, of course this also started executing at time equal to 0 only, which starts, and then after that there's no more statements. That means this finishes the execution. But now if you look at this initial block, okay, so it's just waiting for the simulation time to really reach 300. So like here, so what you have seen, when it comes to 300, maybe it will start executing something. Now at 300 what we are trying to do is we are trying to make this d, right, it's a 1. So here one tick b1 means, okay, so what does it mean? It's a binary 1. It's a binary, right? It's represented using only 1 bit. Okay, so for instance, so I mean it's just a way of representing a logic 1 here. Okay, and then so we are saying that after 100 time units, okay, so this rst equal to 1 tick b1. Okay, rst equal to 1 tick b1. Okay, so here, so one thing to note is that this time you should really look at this way. This statement is started executing at only 300 time units from the beginning. So now looks like, so this one, so do not confuse that it will start executing at 100. So what we need to do is, so this is a kind of a blocking statement. Earlier you have seen this kind of less than or equal to symbol and equal, right? Those are non-blocking. So these are blocking statements. That means this will execute first, and after that 100 time units, that means 300 plus 100 at 400 time units, rst will become 1. Again after, so 300 plus 100, 400 and at 200 time units, total 4 plus 2 600, d will become 0. Again 600 plus 200, d will become 1. So here again 800 plus maybe 200 at 1000 or whatever, again the reset will become 1 tick b0. I'm resetting the reset to 0. Okay, and this is already 1000, right? So 1000 plus 300, 1300. I'm again making d equal to 1, and rst become, I mean rst I'm making again the 1, and again 13 plus 600, 1900. I'm changing the value of b again, and maybe after again 19 plus 5, right, 24. Again I'm making d equal to 1, right? So 24 plus 200, right? Again 2600. I'm making a d equal to 0, and then maybe around, right, 3000. I'm just dollar finish. So here the dollar finish is a kind of again a language construct. It will stop the simulation. Okay, so basically, so if you look at what I'm trying to do here is that at different instance of time, I'm trying to apply different values of d and rst, right? So what are the inputs we have? Clock, right? Of course clock is already given, so you can really play with your d input, right, and rst input. So as long as rst is there, right, depending upon whether it's a synchronous or asynchronous, right? So maybe again ask so whether our design is a synchronous or asynchronous late. So depending upon the signal we have, whether this d and rst, right, inputs, right, their output should change. So what I'm trying to do is that at different instance of time, I'm trying to apply the value of d input and rst input, and I'm just observing q and q bar, and as expected whether the q and or q bar are behaving or not, I'm just checking. So put it in simple words. If you have a full adder design, right, you will have A, B, and C in. For all values of your, let's say, inputs, right, A, B equal to C in, you'll apply 0, 0, 0, 0, 1 and up to 1, 1, 1, and then you will be checking your sum and C out. I mean, the same thing I'm doing here, right? So I mean, that's what the test bench should supposed to do, right? In a test bench, we'll try to, add values, or maybe, change the values at different instance of time, and we'll check the outputs, and even on your breadboard also, right? So that's what, you might be doing it. But of course, this we are doing everything in the simulator, and of course, I mean, we have to write a test bench, to do that. I mean, this is a kind of a typical example of a test bench. So any questions? So I'm taking a little bit time here. So but I think the rest of the example would be, if you understand that one, it will be very, very easy.
So
Yeah.
both the initial blocks will be executed simultaneously, no?
Yes, yes, simultaneous, parallel. Okay.
Parallelly with always as well.
Yes. Okay, but you see, right, the way we wrote, right, this is executed at only time 0. It started executing at time 0 also, but it doesn't do anything, right? This will be effective only at 300 time units. Okay. So I think we will, okay, we'll just undo whatever we did. Okay, just okay. Now if you look at here, right, so there's two files which are really important: d flip flop and a test bench. These are two files. Okay, now coming to the question of simulation, how do we really simulate it? Okay, I think so. I think I also showed this, in my class, that so there are, like, simulators, like, open source simulators like iVerilog. Okay, so what we need to do is just not coming. I'm afraid that is not installed. Okay. Actually, I was doing it in my, it's a virtual box, but somehow Vivoda has some issues, so I couldn't do it. Okay. So by the way, did you try to download a tool called Model Sim and try it with something with that? Sorry, it will take some time, I guess. Just give me 1 second. हेलो यार, तुम गेट पे दे देना यार। वो क्या वो सीओडी है क्या? अरे यार, कितने सार बोले यार, फोन करके आ जाओ, मैं क्लास में हूँ। अब नहीं होगा, तुम कल आ जाओ, ठीक है? थैंक यू। Okay, so let's go on. Okay, so now it's installed. So what you need to do is just like iVerilog. Not sure why it's not coming. DB. Just wait 1 second. Just excuse me. So everybody should able to let's say download this ivory log. So maybe on your, let's say if it is Ubuntu, you just need to type sudo apt get install ivory log and a gtk wave. Okay, so that should do the job. Okay, so you don't have to really do much. Okay, so then assuming that that is done, it's the same thing. It's a bit, it's in a different machine. So what you need to do is just ivory log, there's df.v and the tb. Okay, you just need to let's say kind of compile something like this. Okay, something to your g++, this a dot out will be generated. You look at it, so this a dot out. So then once you write this a dot out, okay, so basically, right, it is printing exactly what you have in the test bench. I think this I forgot to explain, I guess. Let's do that also. The test bench, I think this part I skipped because the file was big. Okay, so what you see here, okay, I just said this is again an initial block, right? Right, of course, till this point we discussed. And now if you look at here, right, there's also one more initial block. Okay, so in an initial block, and there's something called monitor. Okay, and this is a bit contradicting. So this dollar monitor statement should be always in your initial block. But this what this dollar monitor will do, right? What is the monitor? I mean, English meaning it's just monitoring all the maybe the activity or whatever, right? If a class monitor means he will be watching the activities of all the students. But here this dollar monitor means, so what we can have is it's kind of a printf command you can think of. We're trying to really print the the dollar time, again a kind of a standard variable in a Verilog. It's kind of a task. It will print the simulation time. And then if you look at here, right, d equal to percentage b, like you have in kind of printf statement, this kind of qualifier we have, right? So we wanted to print it in a binary format. What is the thing we wanted to print? It's a d, right? So d equal to some value will get it in a binary format, and clock equal to again will get this clock signal in a binary format. Reset, again this reset this map to here, and the q equal to again maybe this q and the q bar. So basically this dollar monitor will print out to your console or kind of terminal whenever if there is change in any of these signals, it will print out everything. Okay, so that is the reason you are able to see these things here. It's saying that okay, at time t equal to 0, that we know, right? D equal to 0, clock equal to 0, RST equal to 0. Of course, this q equal to x and x q bar equal to x. We will see why there's a x. And then at 100 time units, okay, something happened here. So right, again d equal to 0, clock equal to 1, RST equal to 0, and the q value changed, and the q equal to 0 and q bar equal to 1. If you look at here, right, we don't have to look at maybe the two values. So always this is 0 and this is 1. It's always complement. We will see in a simulation what is the reason. But by using this statement, right? We can really print it to the console. Okay, and now uh, someone has a question.
Yes, sir.
Okay.
So the module name that you used, the DOT
Mm,
design and test,
mm.
is it a default name or can we use some other name as well for the module?
So this should be your module name, but this DUT you can just use anything. It's just a qualifier.
Okay, so
You can,
it's like a default good practice, I guess.
and I mean generally we will write DUTR like no UUT unit under test DUT under test, but it doesn't matter as long
Okay,
as you know what you do what you're doing. It doesn't matter.
okay, sir.
Okay,
Right.
okay. So this is like kind of a printing to the console, right? But actually, you see, right? I mean, if one or two signals are there, it's easy to really see on the console. But in general, I mean, we wanted to see the waveforms, right? Okay. Again, if you wanted to see what is this VCD stands for value change dump file. That means whenever there is a change in the kind of any signals, okay. So it will try to dump the simulator will dump into one file, and this is a kind of a syntax. Okay, so you wanted to dump some signals, right? The dump file means the file name we need to mention. I'm just mentioning the DFF VCD. Okay, dump wires. I mean, see, right? So sometimes you are interested in only seeing one or two values. For instance, only D and maybe just a Q, not all. But if you do not give anything, it will try to capture, all the values. Okay, but of course our designs are really small, it doesn't matter for us. But if you wanted to really you know let's say watch only particular signals, we can also mention some variables here. Okay, we wanted to only watch these signals and then those signals will be only dumped. Okay, for instance in this case, right, we don't want to really see q and q bar, but we do not know, right, whether the logic is correct or not. If you know that there's no q bar, just we can just you do not want to really watch q bar, you just neglect it here. Okay, so now since we are done with that, okay, so here, okay, so as I said, so we will generate this file that a.v out, and then what we need to do is just we need to execute this file. Once you execute this file, if you see, right, the timestamp it's generated just now, this dff vcd will be generated, d flip flop vcd, right? So now what we need to do is gtk wave. It's a kind of a waveform viewer. So as I said, there are two tools which you need to install. One is iVerilog and another one is your GTK Wave. Okay, these are this open source DFF VCD. Okay, so now it's a kind of a waveform here. So you just need to click on this one, and then you will see what are the signals it has. Just select all these things and append. Okay, it's showing some signals. This looks like some red here, right? So don't get confused. And that is a 1 second actually. If you see here, right, so now it's showing a kind of a timestamp here, 100 seconds. The time unit it has become 100, this second here. Okay, earlier we mentioned this hash 100, right? Okay, just on a kind of a map to 1 second, but later on we'll use model sim, then it will be some kind of a different timing, but it doesn't matter. It could be second or nanosecond. Okay, now we know, right? So this is a kind of expected clock waveform, right? Just look at this signal clock, right? At initially it should be 0, at 100 should be again 1, and it should stay for 100 time minutes. Again it will be low, high, low, right? This is the clock waveform we are trying to generate. Is that clear?
Yes, sir.
Okay, so now, okay, now let's look at only the reset input first. Okay, so according to our logic is active high reset or active low reset?
Active low. I'm not.
So how many agree with Vaibhav?
Yes,
Our
sir. Low,
logic,
low result.
right? So if you see here, right, if reset equal to 0 and this is getting active, right? Okay, so this is active low reset. Okay, so active low reset means what should happen? Active low reset means what should happen? Whenever the reset is active, that means reset equal to 0, you don't have to even look at your D and all those things. The output should be always 0. So now let's look from this point onwards. Why I'll again come back. If you see here, right, as long as my reset equal to 0, so till this point, right, okay, and of course even beyond that the q equal to 0, right? You see, right, this q, right? So anywhere if you click in between, right, q is not changing, q equal to 0, right, here, this waveform. Am I clear? So because since reset equal to 0, reset has a kind of high priority, right? If the reset equal to 0, whether the clock comes, the positive of the clock is coming here, but I don't really care whether your d input, what is the value of your d input, right? Because the reset equal is there, so the value should be 0. That is the reason if you look at this signal, the q, it's always 0. Am I clear? Okay.
Yes,
So
sir.
now, okay, why the signal is red here? Actually, in general, let me also tell you one thing. So when you open any simulation, okay, if you see something red, not in the beginning but in between, then your design is something wrong. By looking at only the colors we can tell. But of course in the beginning, right, before the reset is become inactive, we can it's okay to have some kind of undefined signal, but in between, so we shouldn't have. Okay, so of course here, as I said before, something, we have still valid, but of course we should have a kind of a justification for why we have this kind of a red signals. And most of the tools, if you see, right, the red is some kind of a problem x. That means, we do not know whether it's a 1 or 0. So now you tell me, why do you think that we have this q equal to x? I mean, I can just simply tell you the answer, but I just want to give some time to think. Vaibhav?
I'm still thinking about it. Maybe,
Okay.
maybe because of propagation delays, maybe it may consider that as well. I'm not sure.
Okay. Okay. I mean, of course.
Maybe because clock is 0 and there is no input before.
Okay. Okay. Snoit, I think, I mean, you're right. So the reason, if you see, right, ours is a kind of a posage clock, right? I mean, the posage triggered flip flop, right? So that means everything should happen. If something should happen, that should happen only at the posage of the clock, right? But if you see, right, clock 0, we don't have an edge here. We started from 0, right? We do not know what is the, and even if you see, right, okay, reset is equal to 0. But now, okay, maybe I'll put in one more question and then I'll ask, I'll try to, explain. By looking at this waveform, can you tell me whether we have a synchronous reset or asynchronous reset?
It's synchronous, sir.
Okay, now Vaibhav, so you tell me why.
So because if it was asynchronous, the output shouldn't have been read, but Q should have been set to 0.
Yes.
Because in asynchronous reset, it is not dependent upon the clock at all.
Okay. Okay. That's perfect answer. So here, what Vaibhav is trying to say is that if it is asynchronous reset, right? So we will not even get this Q, because whenever this reset is, kind of a low, I mean, by the time this Q and Q bar will be already low. But here, since we have a synchronous reset, synchronous means the reset will be evaluated only at the positive of the clock at this point. Now at this point, of course, reset equal to 0. Okay, so the output would be 0. But before this, I mean, I won't be evaluate any reset signal because I don't have any kind of positive of the clock here. Make sense? Okay, that is the reason. Okay, so now let's look at again these waveforms, and I will not explain for all the examples, in much, let's say, kind of very deep. It's again kind of redundant, but at least for this example, we'll see. Okay, so here, of course, at this point, we have a kind of a active clock edge. At that time, reset is evaluated, and the Q becomes 0, and the Q bar become 1. Right? Good. So now let's move to the next clock edge. So some action should happen here. But at this time, if you see again, my reset equal to 0, but of course my looks like D changed to 1. but of course it doesn't matter, right? As long as reset equal to 0, output should be 0. Okay, now let's go to the next let's say clock edge 500. Okay, so here if you see, right, reset equal to 1. Reset equal to 1 means now the reset is inactivated. Okay, now I can respect my D inputs, right? Okay, now if you see my D input is 1, so D input is 1, then Q should be 1, right? Again now I'll go at this, let's say 700. So what is happening? Again my reset equal to 1. Okay, that means I should really see my D inputs. So here if you see, right, my D input is already 0, right? So then my output should also be 0. I'm maintaining that. Okay, again I should go in at 900. This is active clock edge. Again the reset equal to 1. Okay, now I should look at my D input. D equal to 1, so it should be Q equal to 1. D equal to 1 and Q equal to 1. Okay, so again this is my active clock edge, right? So right, so again if you look at here, right, now you see, right, reset it become 0. So now I don't really care what my D input is, right? Because reset has become 0, the output become 0. Q equal to 0 and Q bar equal to 1. Okay, again now if you look at here, right, okay, so my reset is now coming out, reset equal to 1, right? And now of course now I should really respect my D input. D equal to 1, so Q equal to 1. Okay, so now at 1500 seconds, okay, my reset equal to 1, right? Of course my D equal to 1, so Q equal to 1. Again it's 17, right, 100. So again my reset equal to 1, of course I should look at my D, still D equal to 1, I will maintain Q equal to 1. So here again reset equal to 1, but of course this time D changed to 0, so the Q should be changed to 0. Okay, and similarly you can just it will be 0 here, again it will be 0 here. Okay, this clock edge, and now if you look at again this clock edge, so this uh, reset equal to 1, right? That means I should respect my D input. So D equal to 1, so then Q should be 1. Again the 2700, right? So again reset equal to 1, right? So D becomes 0, so Q should be 0. Okay, and if you see, right, at 300 3000 3000 time units, the simulation should end. So we're just ending the simulation, right? So according to our so right, so if you just count, right, so 300 to this total 400, it will be almost, let's say, 3000 time units. At time we have this finish, right? It will be just ended. Okay, that's what we have. See here, right? So what is the purpose of writing a test bench, right? So we need to write the test bench in a way that, so you should check the functionality of RST, and you should check the functionality of D equal to 0 and D equal to 1, and with respect to RST and right, RST equal to 0 and RST equal to 1, all the combinations we checked here, right? So here, why especially this kind of arrangement of these signals, right? I just wanted to make sure that so all the combinations are checked. Okay, so do you have any questions?
No, sir.
Okay, right, so basically you need to use this simple iVerilog and just GTK wave. Okay, so of course this is my Red Hat machine, so in Ubuntu also you should be able to get iVerilog as well as this GTK wave. Is that okay? These two tools you need to really install, and just it's very simple compiling. Okay, good. So just I will move my virtual machine. Okay, so now let's quickly remember I said I will show you a different tool also, right? So model sim, and actually you can also really download the student edition of it, and up to really some kind of a bigger designs it can really work. Okay, so here, so maybe I'll try to do it from the beginning. Okay, so generally, so we should really check whether you have the tool or not. So I just okay, the tool is installed here, so I just wanted to make sure that it is there. Okay, so what we need to do is just, this is a way of opening the model sim tool, so vsim. Okay, Okay, so earlier I did some project, right? So that is open still, so I just need to close that. But if you open for the first time, you don't have to do anything. Okay, now in this case, so what we need to do is we need to create a kind of a new project. Okay, so look at this directory. So I'm just going to have this in this directory itself. Okay, so I'm just earlier I had a kind of a DFF project already. I'm just giving as a DFF2, then a directory will be created. Okay, so you need to just create this project. Okay, and then we need to really to this project, so for the simulation project, so you don't have to really write a new file because you already written the code, right? You just need to select them. What are the files you wanted to have? You just select them. Okay, so here like you don't need to copy, just reference from current location means they are just read from this location. But if you copy, then they made a copy into this directory. Okay, again it's a duplication, you shouldn't do it. Okay, so then just close it. So here what we need to do is just we need to compile. So in iVerilog, hello, who is that? Do you have any question? Okay, so in iVerilog, right, on the command line we are trying to, let's say, compile, right? So something similar here. Suppose if you have any kind of syntax errors or anything, right, so that will be shown here as well. Okay, but as of now we don't have any. Please excuse me, I'm just getting a call. I just answer my phone. So I'm back. So what we need to do is first we need to compile. Okay, and then we need to do a kind of a simulation. So for that, simulate and start simulation. Okay, and then it will open this start simulation directory. So we need to really select the test bench. Okay, and be careful here, there's something called enable optimization. So we need to click on this one. So here, I mean, why I'm trying to, I mean, maybe I can explain. If you look at, right, our test bench doesn't have any input output ports, right? If you click this enable optimization, what it will do is that, okay, there's now signals which are going out of your test bench module. So then it'll try to just take it out everything. It doesn't simulate anything. But in fact, actually, the test bench, of course, doesn't have any inputs and output which are going outside. But in the test bench, we have few signals we are generating, and they are getting applied to your actual D flip flop, right? So we shouldn't, enable optimization. But of course, if you do, if you do not click this, if you, I mean, do not click this one, so you will get an error here saying that okay, the design being get optimized, and it is asking you to do something else. So to avoid all those things, so what we need to do is, so here maybe I'll again click here optimization control, apply full visibility to all modules. That means it's a full debug mode, then it will show all the signals. Okay, it just remember it, and that's all. Nothing we need to do. So here, and then by default it will open few things here. Okay, so here it will open up and again show these signals. You just add it to kind of a wave here, add to wave. Okay, selected signals. Okay, and then now you need to run your simulation. Run minus all, then it will ask you wanted to finish, then you just simply say no. If you say yes, then it will quit and you won't be able to see the waveforms. Okay, here now I just undock this one. Here. So there should be kind of course zoom here. So here if you see, earlier in our that iVerilog, the GTK wave, right, it was showing as 100 seconds, right? But of course, this simulator has a default time unit of 100 nanoseconds. Earlier, it was showing as 100 seconds. But as I said, it doesn't matter. It's a simulation, right? So now what you'll do is, so you'll see all the signals which you are able to see there. Now, at least in this tool, I mean, if you wanted to order generally, right? So I prefer to have something like this. Clock should be always in the top signal. So you can just reorder the signal RST, right? So for instance, as long as RST equal to, so here, right, 0, I don't have to really look at my signals. So till this point RST is 0, right? So now the Q should be 0, right? So here, if you look at here, the Q is always 0. Again, now at this clock edge, which is active clock edge, now RST is already 1. So now, I should look at my D input. D is already 1. D is already 1. So if you look at here, the D is already 1. So the Q should change to 1. Q should change to 1. Okay. And again, so if you look at, right, this is exactly the waveform which you have seen in the that GTK wave. But what we did was we just used model sim simulator, and as I said, it's also kind of a student edition is available. Okay, so you should be able to also do it with using that. And so please mute yourself. Okay, and if you need a bit more explanation to this model sim tool, how to create the project and all those things, if you wanted to know a little bit know about what is this waveform editor and all, I just quickly showed what you need to do. But if you wanted to really wanted to do more, what you just you just type in YouTube, just tutorial using model sim, and you will let's say find n number of tutorials. Okay, you can just really watch them, and otherwise it's a kind of a reproduce whatever I do, it's a kind of a reproduction of what they did it. So just you can look at your YouTube for any more details on how to use model sim and how to simulate it. Okay, so that's what we did now. Okay, so what we did was D flip flop, we use design, let's say simulated using iVerilog and as well as model sim. Okay, now the next thing is that, so what we'll do is we'll try to uh, do something with kind of a Vivado. Okay, now so for that purpose, okay, here, okay, so what do you see now? Do you see the board?
Yes, sir.
It's a full screen, right?
Yeah.
It's a full screen, right?
Yes, sir.
Okay, so I think, I mean, I don't know how far you remember about the board. I just wanted to again explain few things here. Okay, so I mean, actually I'm not able to see the video of mine itself. Maybe let me see. Okay, so now, so like in the middle what you see, right, so this is your actually the Vertex FPGA board, I think, right? So I mean, this is actually the main, let's say the kind of a part of this board. And then, so as I said, FPGA is nothing but your field programmable gate array, right? That means, so the functionality of this IC can be changed, right? So as you, I think you might have done, right? So maybe full adder and everything you done, and you dumped into the code into this one, right? So that time it is really working as full adder. But now today, what we'll do is we'll try to make this whole chip as a kind of a D flip flop. And of course, as I said, it can accommodate much more logic. But as I said, we'll just use the for the functionality of D flip flop itself. And then on this board, right? So we have these 16 switches, right? The 16 switches we have, and maybe when the switch is kind of it's let's say the logic 1, and maybe if the downside it's a logic 0. So basically, as I said, in a lab, right, most of the time you might be wanted to apply it logic 1, logic 0, right? So then for your full adder, for instance, you can map your A, B, C to these 3 switches, and you can really apply different combinations, all zeros to all ones. you can just change the switch positions. Okay, so if you could really see, I'm not sure. So whether the small LEDs, right? I think you still have a kind of a try to recollect. So we have this total 16 LEDs just beside these switches. So here the outputs, right? Outputs we just wanted to see, right? So when the LED glows, it's a kind of a logic 1, and the way the LED is off, it's a kind of logic 0. Am I clear? Okay. And then so for this lab, so what we also do is we'll use is we have these push buttons. So the push button is different from the switch. So once the switch is on, it is continuously producing a logic 1. Okay, but the switch is bit different. The switch is bit different. Okay, so when you press, let's say for some time, okay, and it produces a 1 as long as you press, let's say press it. But once you release it, okay, it will be 0. Okay, so I repeat, there is a difference between your this switch. This is called as a push button. These are like 5 buttons which you have here, right? So there's a difference between these two. So this is the switch, right? So as long as it's in one position, either it's 1 or it's a 0. But push button is a bit different. So when you press, it will produce a kind of a pulse as long as you press, and when you release it, it will become 0. Okay, and then of course maybe in the next labs and all, you will be using these, let's say 7 segment displays. So I'll come back to this later. And then if somebody needs some kind of extra circuits, we can also connect these to these, let's say 4 kind of a pod connectors. Okay, so and then we can use it. Okay, and then we also have some kind of a let's say VGA, let's say port here. So we can generate some kind of a VGA, let's say output here inside, and then we can connect some VGA cable here and display it on the monitor. Okay, and then there is something called USB, something is here. So anyway, that doesn't matter for us. So we'll not be using that. And then, so first of all, right, of course we need to switch it on. So once you switch it on, then there's a kind of a power cable here. So right, so that you will see here the power, the red one. So this will be on, right? So you can see here. Okay, now what is happening is that, so once you switch it on, so there's already some kind of a program here which is running. Okay, suppose you wanted to take this board to a field, but you do not want to carry your complete desktop, right? You can program it on everything on your desk and load it into a small memory here. So I'm not sure whether this is the memory chip or not. So I need to check. I think this is a memory chip. Okay, this memory chip will hold the configuration. What functionality this FPGA has to do, that program you can really let's say load here. So later on we'll see that bit file or whatever, that we can load it into this memory chip. And then now this jumper connection, right? This jumper is in a way that first of all it will always try to load it from this memory, and this jumper connections we can change it, and then we can also erase it. We can do that later. But as far as this lab is concerned, I just wanted to let you know that once we switch it on, there is a memory here, and in this memory there's a kind of a predefined program is loaded, which is just displaying all, let's say, zeros to ones on all the LEDs, and it goes up to 999 and it'll come back. All zeros ones, all ones, twos and threes, fours, and up to 99 it will display and it will come back. So that kind of a program is already pre-written into this, let's say it's loaded already into this memory, and this FPGA is getting configured from this memory in the beginning, and that is the reason you will see this default program. Am I clear? But now when we let's say do our design and dump our program into this, let's say FPGA, so we will see these changes. Am I clear?
Yes, sir.
Yes, sir.
Okay. Okay. So now, we will go to my screen. So again, I'll start sharing my screen. I think I'm a bit slow, but don't worry. It's good to Okay. So here, as I said, the tool which you are going to use is the Vivado, right? Right. I wanted to make sure that the Vivado is installed, right? So I just open this Vivado tool. Okay, so for only this one of this example, we'll just do it kind of interactive, and the rest of the example you should try on your own. I mean, once you get once one example right, the rest of the example is really easy. Okay, so here of course, so what we need to do is we need to really create the project. But of course, if you see right, I already created some projects, so I don't want to open that one. So just to make sure that you also get everything. Okay, so I think at home you won't be able to do this, right? So then I mean, just listen carefully and that should be enough. So in your report, I think it's good enough that you simulate it and show it and answer some questions which I ask in the report. That's enough. But this divider part, right? I think I think if you are here physically, we should expect. But so just uh, listen to it and that should be enough. Okay. So I'm just creating another project so that not to overwrite my previous one. Okay. So this project name. So basically we are going to give an RTL tools, right? RTL files. So it's the next. So then I don't have to write the RTL code. I already have it. So here, of course, the test bench we don't give, right? Because the test bench we are going to use these signals, right? Like the switches and the push buttons, everything. We're going to use it, right? So here we only just need to take the design because the stimulus will be applied in a real time using these switches and all those things, right? So here we need to only take my original design, the design under test, I mean the DFF. Okay, I'm just taking that one. That's fine. And then so hope you remember what is a constraints file, right? That constraint file also we need to add it. So I already kept it somewhere here. So in the this right XDC file. Okay, this basis 3 XDC file, and this is one of the important file. Okay, so then I added that file. I'll explain that. We'll see that later. And then we of course this Vivada, right, will support different boards, right? So we need to go to this boards, right? So this board is from Digilent. Okay, you need to select Digilent. I'm sorry again. Chirag, I'm in a class. I'll call you back later. Okay. So this is Digilent board. So it's a basis 3 board, right? So otherwise, of course, no. Here, if you see, right. So this basis 3 board has a particular FPGA. So we need to know what is the FPGA, the number. Of course, if you search basis 3 documentation, you will get it. So you can just also choose the FPGA, but why not? We have this flexibility here. So we can just simply say, okay, it's from Digilent. It's a basis 3 board. Just next, you don't have to really remember what is the FPGA and all this type. Okay. So it's saying that okay, this df2 will be created. So you just finish. It's creating a directory in your let's say the file system, and let's try to initialize the project. So let it finish. Okay, now meanwhile you tell me, in the past also you have used this XGC file, right? So what is this XGC file? Hello, somebody should answer please.
So like it has information of which port will be connected to which pin will be connected to which variable kind of thing,
Okay.
including clock and switches.
Okay, good. Good. Thanks, Neha. So maybe I'll just add a little bit more to what Snehita explained. Okay. So here, if you see, right. So what I said was, so what we have is an FPGA, right? Right. So FPGA, of course, you're trying to really make it as the field program. I mean, it's of course it's a field programmable, right? So sometime it will work as a full adder, sometime it will work as something else. Okay, now let me say that okay. So this is your, let's say, FPGA. Okay, so now it has, let's say, let's again we'll take an example of your full adder. You're trying to have this A signal, and you're trying to have this B signal, and let's say C in or C, whatever, doesn't matter. Okay, and you have your C out, and you have a sum signal. Okay, now I wrote a Verilog program for your full adder, and basically I wanted to dump into this FPGA which I've shown before. Now in a simulation, what we did was, okay, for A we connected to maybe capital A or capital B and capital C in, and then C out and sum we are watching out. In the simulator also, the simulator is trying to generate, different combinations of A, B, C, and then we are watching this sum and C out. The same thing we have to do it here, right? But the FPGA is somewhere in the middle of this one, and your switches, right? By using switches, you wanted to really apply. By using these switches, you wanted to really apply some value to the A and some value to the B and some value to the Cn. If you try to recollect the picture of your basis 3, right? You have total 16 switches, right? Maybe out of that, some switches you wanted to really connect to either maybe one switch to A and one switch to B and one switch to Cn. And then maybe you wanted to really watch your C out and sum on to one of these LEDs, right? So how do we do that? Okay, so basically what this XDC file is trying to do is that, okay, let's say you have this ABC in signal. So this ABC is in, the XDC will allow you to really connect A to maybe one of the switches and B to some switches and C to another switch, and then the C out and sum to some LEDs. It's not necessary that you have to always choose, the first two LEDs, but in the XDC files, those are the first ones. We always choose that one, but you're feel free to connect it to any of the switches. So basically, the XDC file will make sure that, okay, the inputs outputs of your Verilog design are accessible to either LEDs or to your let's say the switches or your to your push buttons or your this BCD 7 segment displays, right? That one, or maybe you have this pod connectors, right? I just explained, right? So these connections you can really mention your XDC file according to your needs, and then the the tool will route accordingly, right? So of course it's everything in happening in the software, right? Of course, there are some kind of switches which will program so that the respective connections are really made. Okay, so these connection, your intended connections, you need to really mention in your XDC file, and then the tool, the rest of the job the tool will do for you. Okay, it's a way of specifying your intention, which pin, which signal needs to be connected to which switch, or which output should be connected to LED, something like that. Okay, so am I clear?
Yes, sir.
Okay.
Yeah.
Okay. So now if you look at here, right? So now we added the sources, and the file got created. Again, you will see the file here. Okay, and now if you look at here, the constraint file came here. Okay, so now this is your basis 3 XDC. I just undock it so that you see in the kind of a bigger. Okay, so I think I'm not sure. Are you able to see?
Yes, sir.
Okay, okay, now if you see, right, so in this file everything is commented, right? So now you see some section called how to handle the clock signal. Okay, so in this lab we will not touch that one. Okay, and there are some switches. So here the switches section is really talking to the 16 switches we have. Okay, so for each switch you will have two statements. Okay, so here they're saying the switch 0, right? We'll see what is the switch 0 and all. This is a switch section, and we have this LEDs section. That total we have total 16 LEDs, and then so this is a section which is corresponding to your 7 segment display. If you wanted to do with that something with that, and then there's something called this buttons, the push buttons which I explained, the 5 signals, right? The 5 buttons. You have this section here, and then if you see, right, that PMOD headers which I said, right? These are the PMOD header. JA, Jack, they're like total 4, right? 1, 2, 3, 4. So the PMOD headers we have here. So I never used those things. Okay, so yeah, there's a different thing. Listen, then if you see, look at, right, so here the VGA connector is also there. So maybe you're generating some kind of a VGA signal. So now this VGA connector is there, and which pin needs to be connected to which one, right? The VGA has this H sync, V sync, and RGB signals. So those signals we need to really connect it. Okay, anyway, we're not going to use it, and we also have this this RS232 serial interface here. the metal one which is shown in the earlier video, right? So this USB R232, and we have a couple of other things. Okay, so basically we will not use many of these things, but at least for the labs we will use the switches, buttons, lids, BCD 7 segments, at least that we will use. Okay, now in this section what we need to do is a couple of important things, right? So first of all what we need to do is we need to go to our switches. Okay, and then so how many signals you have, right? 3 inputs you have, right? I repeat, so we have 3 inputs, right? What are the 3 inputs? D, CLK and
D
reset.
of reset.
Okay, so now first what I'll say, okay, now I'll do that. Okay, as I said, so maybe if you uncomment the color will change and we'll see. If you look at here, this package pin V17, right? Why this V17 means, of course, if you look at on your basis 3 number near to the switch 0, it's a V17 is written. Okay, that is a number actually here. Okay, that means he's saying that okay, switch 0 is nothing but your V17. So that's just a kind of a I mean the hard coded here. Of course, according to the board it will change. Okay, are you following what I'm saying? So this V17, if you look at your basis 3 board, okay, near to the switch 17, switch 0, this V17 is written. That's a kind of I mean just indication for us. Okay, so now, so here I mean when they are creating this file, so they assume that okay, you have a kind of a signal name called switch 0 in your design, but in our design what we have, D input, right? So just we need to change that to D input. And similarly here, so for each, let's say switch, you have a 2 pin, let's say 2 statements, set property. Okay, these 2 statements we need to change. So here again, so there is something called LV CMOS 3.3 signals, or it's a 5.5 volts or whatever, but generally this basis 3, right? So the IO standard is LV CMOS 333. That means all IOs are like 3.3 volts. Okay, if you do not understand, it's fine, just remember that we need to just change these 2 signals, and of course what is important is only this V70. Okay, so right, so as I said, so we need to really change the switch 0 to D input, because our design has a D input, right? When they are just making this file, just they just kept as a kept this placeholder, switch 0, switch 1 and all. Okay, so now I'm on the second line now, right? So I just wanted to make some space here. Okay, now so the other signal, right? Okay, here if you have V16 on the basis 3 board, this V16 is nothing but your second switch. Okay, I'll use that switch. Okay, so we have this our RST signal, right? Please remember, as I said, Verilog is case sensitive, and our D flip-flop code has small d as an input and RST as input. Okay, again we need to change this to this RST. Okay, now the clock signal, right? So we said there are 2 inputs, right? Total 3 inputs, right? So D and RST. Okay, so for clock what I'm trying to do is, so I will not use these standard switches, I will use the push button. Okay, I mean there is advantage of using a push button now, but as I said, the clock which we are going to generate, I mean the clock which basis 3 has 100 megahertz clock, right? And with that frequency, if you try to operate, you won't be able to see anything on the this basis 3 board, right? For that purpose, as I said, so we need to really divide our clock into maybe 1 hertz clock, right? But of course that we will do in the next lab. In this lab, the clock signal also will try to generate using some push buttons. Okay, as I said, these are 2 switches, right? Okay, so as I said, for the clock I'm going to use push button. Okay, so here the push buttons are mentioned here, push buttons. Okay, now here, so what I need to do is, so right, so this is like button C means like the central button. Okay, so U18, and of course we can also confirm, I'm just looking at the basis 3 board. Of course button C, which is mentioned here, the BTN C, okay, is nothing but your U18. Okay, of course exactly U18, and of course our signal name is not B button C, it's a CLK. We just need to change CLK. Okay. Hope I'm clear. Now 3 inputs are done. Okay, now outputs, right? Of course, outputs, of course, we cannot map it to the input pins, right? Of course, for output purpose, we need to use only LEDs, right? So here I'll go, these are LED section, right? I wanted to really see Q and Q bar, right? So that means I need total these 4 lines. Okay, of course, my signal name is not LED 0 in my design, it's a small q, right? So for these two statements, I need to change it to q, right? And for this statement, I need to change q bar and q bar. Okay, that's it. Okay, so now you can apply your inputs, right? D and CLK using switches, clock using this push button, and you can observe your outputs at the q or q bar on these 2 LEDs, and which are near these switches. Okay, later on when I'm simulating, I'll show you again. Am I clear so far? Hello.
Yes, sir.
Okay.
Yes, sir.
Okay. So now, so if you look at this, let's say document, so something is mentioned here. Okay. So if you try to run exactly, like what is mentioned here, you will get some error, implementation error, and if you get that error, okay. So what we need to do is just we need to maybe I'll tell you what I'm trying to do, and then let me copy this. We need to do this. Okay. So I don't know this. Okay. First, let me copy, and then I'll explain. So I think hopefully it gets copied. Okay. So I think underscore did not get copied, so you have to be very careful. Syntax error. Okay. Clock dedicated route false. Get nets CLK. I think again we have a problem with underscore copying from PDF. Careful. So here again, sorry, get nets also not highlighted. That means this is not copied. Okay. So here, I mean, what we are trying to do is that maybe again I can go and have a look at this code. What Vivado does is that whenever you have something mentioned in this sensitivity list, it thinks this is, of course, this is a clock, right? I mean, this is a clock, right? Of course. In general, in a normal design, right? So if you have a kind of a clock, right? So maybe this is your clock. So clock is a kind of a versatile signal or a kind of a global signal. If, for instance, let's say this is your complete IC. Okay, so there might be a flip flop here. There might be a flip flop here. There might be a flip flop here, right? I mean, there's a lot of flip flop in your design. Kind of millions of flip flop. And the same clock has to go to here. Same clock has to go to here. And maybe I'm sorry, bad drawing. The same clock has to go here. So same clock has to go here and here. Right? It's something like that. It's something like kind of you're trying to really distribute this clock to many flip flops. So I mean, if you try to simply distribute, so there is a kind of a lot of propagation delay of because of these wires and all, right? So in general, what we do is in between we will introduce what is known as some kind of a buffers. I mean, this is not an inverter, it's a buffer. We'll try to introduce to reduce this delay, and so that the signal is getting let's say reconstructed. Generally we will use this buffers. Okay, but now in this particular case, so what we wanted to do is that, I mean, we do not need these buffers. This is not, we are just seeing, see, in general the clock we shouldn't route it to this push button, but we are trying to route it to this push button, right? So then, so I mean, what I want to say is that if you look at this property, right? So what we are trying to really write is that clock dedicated route. Okay, of course, right? It will think that the clock is a kind of a global signal. So we are saying that okay, don't use any let's say buffers and route these signals. So then it will be easily routed to this button C. Okay, but in general we shouldn't do these things. So in general, in your real design, we should not do this, because the clock is really driven from your FPGA itself. But in this particular case, we wanted to simulate our clock using this push button, right? So for that purpose, I mean, we are just doing it. So we are just trying to really tell the tool that okay, don't use a kind of a dedicated routing for this clock, a clock dedicated route. Okay, it's a false. Okay, that means it will not use any buffers or anything else. Okay, just it's simply routes like a kind of a signal, like your D and RST signal. Okay, you need to just add this statement here, then you're set. We can go back here, and then so we just need to run our synthesis. So it will take maybe 1 or 2 minutes. So do you have any questions so far? Vaibhav?
No, sir.
Okay. So I think I presume that there was a kind of a very detailed PDF was let's say distributed to all of you about different steps, I guess. So I think with using a half adder or a full adder design. Okay, the same thing I'm trying to do, but extra thing is only this set property clock dedicated route. I just said, so the Vivado by default, whatever in your let's say always sensitivity list. Okay, when you mention this pause edge, right? It will think that the what is followed by that will be kind of a clock. Okay, and it will try to use some kind of a dedicated buffers, and it will try to route that signal. And then it's tough for us to really reach to this button C, right? We just wanted to disable that, but in general design we shouldn't do it, but it's a simple single flip-flop, right? So it's just we can do that for our purpose. Okay, so now it's like still running synthesis, so it will complete in a minute or two. Okay, and then so I mean, let me ask you this question here. So what do you mean by synthesis here? I think I tried to explain, I guess.
So if I remember correctly, it was like we have written the code in a behavior model. It'll now it'll take it to a less level of abstractions,
Yes.
and with the given things it has on the board, it will
Mhm.
try to map the function of the higher abstraction level to the lower one,
Mm-hmm.
and then we can run it on the FPGA.
Okay. Okay. So again, please excuse me for a minute. COD है क्या? अरे यार तुम फोन करके क्यों नहीं आता यार? So I'm in a class. I cannot come now. आप कल सुबह आ जाइए. ठीक है? Hello. Yeah. Vaibhav, I think your explanation is like 100% correct. But just to add on that, so I just wanted to, and again, for the sake of everyone, I just wanted to clear a few things. Okay. If you remember, like we said, let's say if this is your FPGA, right? If this is your FPGA, let's say, of course, FPGA contains what is known as CLB, some kind of a switch matrix, and all those things. But we can just explain in a kind of a different way. So we have this FPGA, and assume that there are some flip flops, some standard gates, some OR gates, XOR gates, whatever you can think of. Okay, NOT gates. You can just think of all those things, and then the connections are really programmable. Okay. Now, what Vaibhav also said is that this FPGA is nothing but some kind of a sea of gates where you can choose the gates you want and the connections the way you want. Okay, what exactly this synthesis step is trying to do is that okay, you have written a kind of a Verilog code here. Okay, maybe this code will get synthesized to a flip flop and maybe some kind of a AND gate, OR gates, or a kind of XOR gates and different things. Okay, so what this synthesis step will do is that okay, uh, please excuse me again. Okay, so okay, what this synthesis step is trying to do is that, so what kind of let's say gates I need to really implement. Okay, as I said, from this sea of gates, so what are the things I should use it? It's trying to really figure it out. That means your let's say higher level of abstracted design is getting mapped into the cells which are available on the FPGA, in simple words. Okay, now the next step, right, run implementation, right? Okay, now it's, try to figure it out, this blocks and this block I can use it. And in the run implementation, so what is this place and route is also route, I mean it's performed. So that means the connection between these, let's say, chosen this thing, right? So I have to really route them physically, right? So that's what, it's this, implementation step is doing in a simplistic terms. Okay, but of course, if you do some kind of advanced courses in future, so you'll also learn more about, this FPGA, what the FPGA contains, the CLBs, LUTs, kind of a switch matrix. So but for your course, I think maybe this should be sufficient. You need not really understand, what exactly, the content of FPGA and, how it works. Okay, good. So we limit the discussion to that point. So now I think it should be done. Do you have any questions further? So in the op design step, maybe it's trying to optimize the design, and then it does what is known as the place and route. Okay, so then try to find out, the kind of routing resources on the FPGA and all. See, right, sometimes, maybe your FPGA contains like, let's say 100, let's say some cells, but your design needs maybe 200 cells, right? So when you are doing synthesis, right, it will automatically tell you that, okay, I try to map to the existing available, let's say cells, but of course I need these types of, cells, but I could only find this. Maybe if your design is too let's say big, it will not be able to fit it. Similarly, in the place and route step also, I mean you have a small design which it can fit, but you have too many connections between these, let's say cells or gates, and then again I'm not able to really find out the connections between this point. Of course, logic wise I'm able to map to uh, logic wise I'm able to really map to let's say your design, but okay, in terms of the connections or maybe the, routing the kind of a signal connections, I'm not able to really find enough resources for routing. Then that time also it will fail. Okay, let me see. So what is this error? One second. I think you see, right, we did a mistake. As I said, when we copying from the PDF, right, that underscore is not getting copied. So the correct syntax of the signal is that, the syntax for this command is clock underscore dedicated underscore route. Okay, so which we forgot to copy it. Okay, that is the thing. So we have to really rerun again. So basically what we'll do is, so we will not rerun again, we just close this project because it's the same thing. I just do not want to waste time. So I'll open the existing project which I did it before. Okay, so generally it will be with this XPR. I'm just opening that project just to save time. Okay, so now once you run implementation, right, so there's something called generate bit stream. So basically that time, only that time, so I mean you need a FBC3, right? Once you generate the bit stream, right, so it will be generating a kind of a file, a programming file for your what do you say, the basis 3 board. Of course the same design we can use some other boards, Nexus board or anything, right? Of course that time, you might have chosen, your project settings a different board. Okay, basically in the generate bit stream, the tool will try to generate a kind of a bit file which you can use it for programming the FPG. Okay, so now what I'll do is, I think I generated already the bit stream. Again, it's just kind of a click, you can do that. So we can just do this hardware manager. So now here I'm trying to really connect it to my FPGA which is shown here. Right, open auto connect. So it's already there. To my desktop it's connected. So that is the reason it's able to detect this FPGA here. Okay, you just need to it will really show the FPGA here. If you remember, right, so in the beginning I was telling that okay, if you know the FPGA number, you can just choose instead of this basis 3 board. Actually you can see this FPGA number here, XC7A 35T0. Okay, but anyway, so it doesn't matter. So now what we need to do is this program device. Okay, so now here when you click on this program device, so here if you see, I mean this is my directory where this bit file was generated. Right, it knows where is this bit file. It's a name with a dot bit. Right, if you just say it's a program, this bit file will get copied to your FPGA. Okay, and then okay, now this is programmed. Okay, now I'll just stop sharing so that you'll see my this thing. Okay, Jayesh, now you're seeing the basis 3 board, right?
Yes, sir.
Okay, it's now full screen, right?
Yeah.
Okay, you see, right, earlier it was showing some automatic numbers, right, like all zeros, all ones and all, right? So that is a kind of a default program it has. But when I did this program device, the bit file was copied and this FPGA is really programmed now. Okay, now if you look at here, right, so here as I said, I think you're able to see the switches, right? So here the first switch we mapped it to clock, so as a D input. Okay, and the second switch we mapped it to RST, right? Hello.
Yes.
Okay, if you are confused again, we have to look at our maybe the XDC file. Okay, the first switch is our D input and the second switch is our reset. And then if you look at this central switch, right, this button C, we mapped it to clock. Okay, so now for instance, right now the clock, this push button is not pressed. That means the clock is really 0. Okay, when I press this clock, what will happen is that some kind of a clock signal will be coming, and when I release this push button, again it will go to 0. For instance, if I mean in the real design, what is happening is that now, so if you see, right, this clock is coming. Now I'm just pressing, right? So that means the clock signal equal to still 1. Maybe you're not able to see that I'm pressing, but my finger is on the center button. Okay, if I release, the clock will become 0, and again when I press, the clock is 1, right, and it will become 0. But now the moment when I press, right, so what is happening is that the pause edge of the clock is getting triggered, right? See, when I press, it will become 1, right? So now as long as now if I do not press, it's 0. When I press, it becomes 1. That means a pause edge will be triggered, right? So I press 1, pause edge will be triggered. Okay, so that's how I'm simulating my clock here. As I said, in general we will use the FPGA clock, but it's 100 megahertz, we cannot use it, right? So for this lab, what we'll do is we will use this push button, right, for clock. So whenever you press, there's a clock signal applied. It's a clock equal to 1, and if you release, the clock equal to 0. The moment you press, there is one pause edge is getting created, and as long as this is 1, it's a clock equal to 1, nothing will happen. Okay, so now do you see that one LED is blinking?
Yes, sir.
I mean, it's not blinking, of course, it's constantly on, right? Okay, now if you see here, right, the first LED we mapped it to Q, and the second LED we mapped it to Q bar. Okay, now if you see, right, the switch positions, D is 0. Okay, D is 0. Okay, maybe of course with this press and all, I already applied the clock or whatever, and at that time the reset is 0. Right, is reset equal to 0 means the Q should be 0 and Q bar should be 1, right? And that is the reason the second LED is now glowing. I repeat. So of course with this button I pressed a couple of times. So that means the reset already got evaluated, right, at the active edge of the clock. And since RST equal to 0, RST equal to 0, what happened? The Q become 0 and Q bar become 1. Okay. Now what I'll do is I'm making this second switch equal to 1, RST equal to 1. RST equal to 1, but the LEDs are not still changing because my active clock edge is not coming. I change this reset equal to 1, okay, but LEDs are not changing because my active clock edge is not coming. But when I press this button, I am not pressing now. When I press this button, my active clock edge will come and something should happen. Now if you see, right, let's assume that if I press, what should be, I expect, since D equal to 0, here, okay, again D equal to 0, Q equal to 0, and the Q bar equal to 1. Even now if I press clock, nothing happened. Since because reset is now inactive, that means the D value should be respected, but of course D equal to 0, the Q equal to 0, and Q equal to 1. You see, right, even if I press, there's only one let's say passage up, let's say occurred. If I press again one more clock, let's say passage. If I press one more time, one more passage. But now this time what I'm trying to do is that, right, if now D equal to 0, right, so I press, I'll make sure that the D equal to 1. Now D is in position 1, but of course it's not getting affected because we need an active passage clock. Now if I press this button, so what should happen is that if I press this, you're still seeing my screen, right?
Yes, sir. The LED
Okay.
should flip.
Yeah, now it's nice. Now if you see, right, if I press 1, so the Q should be 1 and Q bar should be 0, right? So now
Yeah.
I'm pressing still, but I'll still release it. Now if you see, if I press how many times, right, it doesn't matter because you see, right, active clock edge is coming. At the active clock edge, reset is not active and D equal to 1, right? Of course the Q is always 1. Even if I press so many times, nothing will happen because it's a right value because D equal to 1. Now again if I change it to D equal to 0, and if I press the clock, so again it should reverse. It's reversed, okay. And again now this time if I press so many times, maybe the clock doesn't happen because you see, right, again D equal to 0. Again if I press it, D equal to 1, and if I apply clocks, now it's D equal to 1. Now let's see, now D equal to 1, right, okay. Now I'll wanted to make sure that the reset equal to 0. I'm making reset equal to 0, but now if I press any clock, because since now reset is active, again it should change to Q equal to 0 and Q bar equal to 1. It changed. Now you see, right, even if I press so many times clock, doesn't have matter because your reset is active. If reset equal to 0, your output should be 0, Q equal to 0 and Q bar equal to 1. So now are you convinced that it's working as a D flip flop with a reset?
Yes, sir.
Okay. So in this
Yes,
way,
sir.
you need to really simulate all your designs. Okay. Any questions? Okay. So now, so what I'll do is quickly, okay, so I'm not showing, or maybe I found I can share again screen. So you're seeing my screen, right? So
Yes,
similarly,
sir.
okay, so similarly, so maybe we can finish this part and we can go to the other one. So close this project. I'm just closing. Okay, so project open reset T flip flop. I'll show the functionality here. So something similar, I have a T flip flop code I'll show later. So I also did everything. So I'm just again opening the hardware manager, open target, auto connect. Okay, so program device. So now the Steve already generated. Okay, I'm not sure whether it's done or not. Okay, it's programmed. So I'll switch again to, okay. So you're seeing the basis 3 right now. Yes.
Yes,
Yes,
sir.
sir.
Okay. So now if you see, right, now I mean I don't remember what okay, so now T flip flop, right? Okay, T flip flop will have how many inputs? One T input, right? I mean one T input, of
T
course.
clock reset.
T clock reset, right? I think I mapped the same way. The first input is your T, okay, and the second input is your RST, okay, and then the clock is again in the middle, okay. So now here, since reset equal to 0, right here, the switch is closed, your Q equal to 0 and Q bar equal to 1. That is the reason this LED is glowing. So now if you see, right, even if I change now, this is my T input, nothing will happen, right? Of course, the clock is not coming. That's one reason, and of course the reset is active, right? So as long as reset is active, if the clock comes also, nothing will happen, right? Clock comes also, nothing will happen, okay, because reset is active. So what I need to do is, okay, I wanted to make sure that T equal to 0, T equal to 0, I'm making the reset equal to 1. That means now reset is becoming inactive, okay. So now if I press the clock, what will happen? So current state is 0. If I press clock, what will happen? Nothing will happen, because the T flip flop, right? T flip flop, as long as your T input is 0, as long as your T input is 0, it will just maintain the current state. Is that right? What is the current state? Q equal to 0, Q bar equal to 1. It's just maintaining it. So now I'm applying clock so many times, nothing is happening, because the present state of your flip flop, T flip flop, is Q equal to 0, Q bar equal to 1, and nothing is changing, right? That behavior we are testing here. But now what I'll do is, now this T input I'm changing it to 1. So if the T input is changed to 1, what is the behavior? Hello, it should toggle, right?
Yes, sir.
Okay, now if I press clock, it changed, okay, it will remain in the same state. Now as long as T equal to 1, right? So you see, right, of course now, of course T equal to 1, but of course not active clock is coming, right? So if I give clock, again it change. If I click clock, it will again change. You see, right? So whenever the clock comes, right, as long as the T input equal to 1, it just toggles. If it's T, I mean, if present state equal to 0, it will become 1, and if it is 1, it will become 0 whenever the clock comes. You see, right? That is the reason if I'm just giving some clock pulses here, the positive of the clock here, so it's always changing 0 to 1, 0 to 1, 0 to 1, 0 to 1, because T equal to 1. The behavior of the T flip flop is, as long as T equal to 1, it will complement its states. If it is 0, it will become 1. If it is 1, it will become 0. See, right? That is the reason you're change, see this change in the LEDs. You're able to see?
Yes, sir.
Yes, sir.
Okay. So now if you see again, if the reset equal to 0, if the clock comes, so the output should be set to reset to 0. Right? I'm just giving the clocks, but reset is active now. It should be 0. Right? So that's behavior we are checking here. Okay. So now the main idea is that whatever you do in the test bench, that you are doing in the simulation, but in the sometimes your design might work in the simulation, but if you maybe you will have a problem in working in the real hardware. That is the reason we need to synthesize and maybe map it to maybe the FPGA and generate the bit stream and load into the FPGA, and then you need to simulate your inputs and check it. That's exactly what we are doing now, right? We're trying to change the clock signal, we're trying to change the reset signal, T inputs or D inputs, and all the combinations we are checking, right? So this is what you're supposed to do in the real lab. Okay, is that clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So, okay, so now I think we are just coming to maybe end. I think it's been already long time, but no issues. So if you see, look at, I just wanted to show the T flip flop. So here we said we need to really design our T flip flop using D flip flop, right?
Yes, sir.
So how do we do that? Okay. If somebody asks you to design one flip-flop using other one, so how do you do it? So here, so I mean basically what we need to do is a T flip-flop, right? So we have this T, QT, and this QT plus one, right? The next state.
We'll
So
take the XOR between Qn and T.
yeah, okay. So just yeah, I think I'll be very quick. I think your answer is right. Okay, the QT plus one is as long as you see right T equal to 0, it will be 0, right? 0 and 1. But if the T equal to 1, as I said, the state will be complemented. If it is present state is 0, it will become 1, and if the present state is 1, it will become 0. Okay, now see what we have is we wanted to have the functionality of T flip flop. That means you'll give a T input here, and you wanted to have Q and maybe your Q bar, but you do not have a T flip flop, right? But what do you have
So,
actually?
so we can't see your screen yet. Are you writing it on the whiteboard or something?
Yes, yes. I'm sorry. Okay, thank you. I'm writing whiteboard. Share. Okay. So Vaibhav, no?
So,
Okay.
Yes,
I mean this.
visible.
Yeah. This truth table I wrote, and as I said, this is a block box we have the T flip flop. We wanted to get this behavior, but here we do not have a T flip flop. What we need to do is we have a D flip flop. By using D flip flop, we need to really get the functionality of your this D, right? So that means there's some kind of a logic here, right? We will take this D logic, right? And then we apply some kind of a D input, and then the Q and Q bar of this one is connected here, right? So that means we need to find out what is the logic we have here, so that the same input is applied to D. I mean it will exactly get this QT plus one. I repeat, what I said was maybe we need to really realize this functionality of your T flip flop, Q and Q bar. But we do not have a T flip flop readily available. But what we have is we have a D flip flop. Okay, and this is something like here Q and maybe Q bar already connected. So now in between we need to do something, right? So which will exactly, I mean we need to find out with this what is the logic here. Okay, it will take this T, and maybe this logic also will read this maybe QT. Okay, and then it will exactly give the same functionality which we study here, right? So now if this is the case, you know, like what we have is T and QT. Okay, now we are getting this QT plus one. Okay, and if you wanted to get this next state, exactly this one, what is the input we should apply to the D input, right? What is the, that means here, so we can have one more column, right? So right, of course this D input, right? D input is nothing but exactly the QT, right? The excitation, if you remember, right? So that means I can say that the QT plus one is nothing but your D input, right? So what we need to do is just we need to really simplify your for your this is your T and this is your QT, right? So basically if you look at, right, so we have only ones at this point. So D is nothing but your T exclusive of your Q of T. Okay, right? Is that clear?
sure.
Okay.
Yes,
So
sir.
now, okay. So this I think should be okay. And now if you see here, what we did was, of course we need to use our D flip flop. We are using the D flip flop, right? Of course the D input, right? The D input is not exactly now the D input, but it's kind of a modified one. If you see here, right, we are just connecting to D1. Let's see what is this D1 signal. Oh, D1 is the output of your XOR gate. As I said, and as I said, you don't have to really know much about Verilog. As I said, all the primitive gates are available for you. The XOR gate is a standard gate you available here. So this is I'm instantiating here. I'm just calling it XOR1, and this is a D1 output. And of course, the input is nothing but my Q, right? Of course, this present state is Q and T, right? T is my input. If you see here, right, of course, when you are having this D1, right, you can have this wire D1. Even if you do not declare this wire D1, it's fine. By default, if you do not declare anything and if you use it, the language interprets it as a wire D1. Okay, even you don't have to really have it. So here, what I'm trying to have is that so here we have some kind of a XOR gate, right? So this I'm calling as signal D1. This is my small t, and this is my small q. Okay, please excuse me the bad drawing. So this is getting from here. Okay, and then that's all right. So this is my q and this q bar. Okay, this I'm calling as some XOR underscore 1, right? And if you see, right, of course this is connected. Okay, that's what I have in the code right here. This is D1 and QT, that's all. Okay, so now I mean, so here again we can have TB, test bench, so similarly the way I explained for your D flip flop, I will not go into much details. So here again we are simulating the T test bench T flip flop. So the T input and the rest of the things are same. This time I'm instantiating a T flip flop. Okay, and now you have the signals again, and the initialization for the generating clock and all those things. And I'm trying to generate again a different combinations of T and RST and all those combinations, and I'm just trying to monitor them here. And again also again use this VCD file generation, this one. So when you execute this one, right, so you'll get this VCD file again. So you just need to use GTK wave here, and then maybe this TFF VCD, and then you'll get this file. Okay, so then again just go maybe go this here and select all this signal append. So make you I mean I will not explain again whether it's a valid combination or what. So I think it's valid, but you need to convince yourself that okay, this whatever the output we are getting is the correct one. Okay, so just follow the same procedure and see what are these signals, whether it's correct or not. Okay, and then do it. So similarly, so we can also do this model sim simulation. So I already have a project created here. So I just open this MPF. Okay, so this is MPF stands for model sim project file. So it's already there. So here when you are trying to add here is right, of course we need to add our T flip flop Verilog code, and T flip flop uses a D flip flop, right? That also we need to use it. And then of course definitely we need to have a test bench. These 3 files they already compiled. Of course I am just again compiling again, right? And then simulate, start simulation, and then I said this test bench only we need to simulate it, right? And then as I said it's a full debug level here, otherwise you will not see any signal. So it will open something like this, and then what we need to do is just select all these signals and add it to wave select signals. Okay, so maybe I'll undock it and then simulate, start simulation, sorry, now run simulation, run minus all. It will ask you to finish, say no. Okay, now you'll be able to see the waveforms. So maybe undock it. So now is here you have similar waveforms, and again either use this approach or that approach and just validate the design by as I said, you need to convince yourself that okay, it's working correctly. Okay, so this you can do it. Okay, so again we already have seen the let's say the Vivado, right? That for T flip flop we have seen. Okay, and similarly so you have a JK flip flop. Okay, I just will simply look at the code. Okay, so here I think okay, if you see here, maybe let me just select font. Okay, so here maybe now if you look at your this one, right, of course you can use again your truth table and all to get this equation, but if you see here, right, we have an AND gate and we have an AND gate and an OR gate and a NOT gate. So maybe in your basic Verilog description, you see basically all these gates. Maybe of course this I call it as a D1 net, this I call it as a D2 net, and this is called as a D net, and this I call it as a K bar. Okay. So here if you see, right, let's look at the K bar, right. So it will take the input K and it will produce a K bar signal. So basically I'm just calling this K and this is a K bar. And now this AND gate should really take this K bar, and now if you look at this one, right, basically Q. Okay. So again have a look here. Okay. So basically it's taking Q bar and Q, it's producing a D2 signal. Okay. So basically D2 is nothing but this signal D2, and this is your D1. You can check here again. So D1 is nothing but Q bar and J. Let's see again Q bar and J. See here, so it's taking Q bar and a J. This is a D1. Okay. J, D1 Q bar J, and then the final OR gate, it takes D1 and D2 and produces a D, and the D is connected to the D of your what do you say, the D flip flop. Okay, here that's what you have, right? This is your D1 and D, and you generate a signal name called small d, and this is connected to the D of your D flip flop. D is connected to D flip flop, and the rest everything is remain the same. Okay, hope it's clear. So again, you need to have a test bench JK flip flop again here. So again, see, right, I will not explain all these things. So similarly, you wanted to really test, what happens when J equal to 1, K equal to 1, J equal to 0, K equal to 1, all the 4 combinations, and with respect again the reset. So all the combinations I wrote it here, and then this will print it to your screen, and this will generate the VCD file. Okay, so you can just open your VCD file as the check, or so as I said, I have already created a kind of a model sim project file here, so we can also simulate in the model sim. But interesting would be to really see it on the FPGA. Okay, so why it's not responding? Just let me see. It's not responding. Let me stop and okay. Okay, I think I'm not sure. I think it should respond. Yep. Okay, so now as I said, it was in a background, so I just close this project. Okay, so as I said, I already have this JK flip flop project. I just quickly show. Open recent. So again, you'll follow the synthesis, implementation, bitstream steps, and then so I'm just programming it. So open target, auto connect. So then it should be able to find my okay. So now maybe I'll just do it one more time. Okay. Is my basis 3 visible now?
Yes, sir, it's visible.
Okay. Now if you see what I did, I think if I remember correctly. Okay. So now in this JK flip flop, right? So I think J I mapped it to the first switch, and K I mapped it to the second switch, and the third switch is reset now. Not the, I mean, generally, when the D or FF, we had second switch was the reset, and the third switch was my reset now. Okay, and again the clock is in the central button, and Q is here and Q bar is here. So now, I mean, whatever it is. So now see here, my reset equal to 0, right? Reset equal to 0, right? My q bar is glowing, q is 0, right? So now even if I change j, k, nothing is happening. Of course, it's not because of reset is 0, but of course the clock is 0, right? So now I'll see, right? Okay. So now clock is, if I give, right? So reset equal to 0, nothing will happen. Okay. So let me check actually. So I'm a bit confused. So the only way I should do is that I wanted to check my okay. So I'm a bit confused, right? So which is the one which I used? So what I'm trying to do is it's not allowing me to do. So what I'll do is let it run in the background. Okay, I know it's a JK flip-flop, so I'll just go here. So I think it should be in the sources. So this is running actually on my desktop. I'm using a VNC connection to share it to you so that it will be seamless. So that is the reason it's a bit slow. It's really slow. I should go to the constraints. Of course, yeah. So if you remember, right, in the GUI we are changing, right? Okay. So if you change changing, so that will be should be reflected here. So as I said, I was a bit confused, right? So this we can check. And of course, you see, right? So the first port is first switch is J, and the second switch is K, and the other one is R reset, right? And then the LED is Q, and the Q bar, it's the same. Yeah, it's the same. Okay, nothing else. So here, okay, good. So now, okay, I'm not sharing, right? Okay, good. I just cross-checked whether the signals are correct or not. Okay. So now if you see, right, the reset equal to 0, right? Reset equal to 0. So now, since my J and K equal to 0, what should happen? I mean, of course, the reset is active, so nothing will happen. Okay. Now just we release the reset, right? If the release the reset, what should happen? If now J and K equal to 0, whenever the clock pulse comes, it should maintain the same state, right? Maintain the same state. Okay. So now if K equal J equal to 1, what should happen? If J equal to 1, J is like kind of a set input, right? If the clock comes, it should be set to 1. J or okay, maybe let's see this one. J and K equal to 1, right? So J and K equal to 1, so it should always toggle, right? If you remember the J and K flip-flop, okay. So I think so now if you see here, so I think it's K, right? So it's like a so K equal to 1, it's always 1.
So we are unable to see the LEDs.
I mean, what you're seeing now? You're
The
seeing the
camera
basic.
has, yeah, we are seeing the board, but the
Yeah,
camera has
shifted.
shifted a bit.
Okay, sorry.
Yeah, it's fine now. Yeah.
Okay, I'm sorry. Okay, because as I said, when I'm in this mode, I'm not able to see myself. Now it's better, right? Okay. So I was just trying to explain. So now it's a K equal to 1, right? So it stays the same. Okay. But now if now both J and K equal to 1, whenever the clock comes, then the input should really toggle, right? The output should really toggle. So in both are really 0 0. So right, so it should stay in the same state. Okay, now let's say there is now clock equal to 1, right? So I'm just releasing, now it's 1, but now when the reset comes, of course it will not change, but of course it's waiting for the active clock pulse. So when active clock pulse comes, right, it's a reset. When I release this rate, it will again change because j equal to 1 and k equal to 1, right? So basically in this way we can really check the complete design. Okay, so the maybe I'll just switch to again sharing mode. Okay, so okay, I mean this is what I was just maybe I forgot to when I'm just typing here. So this is the JK flip flop, the XGC file. That's where I checked what is the mapping of the ports, right? So okay, so looks like so there's a mistake here. So this also should be in RST. Okay. Okay. Anyways, so the whole I think I need to really generate again the complete let's say JK flip flop thing. So okay. So nevertheless, okay. So here the whole idea was that just to summarize what we did so far. So given a D flip flop, so you can really come up. I mean, you can of course write a let's say Verilog code for it and a test bench for it. You can simulate is using iVerilog and a GTK wave or a model sim. And now in a let's say model sim or iVerilog, you're writing a test bench to simulate it. Okay, but when it comes to the Vivado, right? So we need to use either switches or maybe these switches or these LEDs. And as I said, generally we'll use the clock which is available here. But if you use that clock, it's 100 megahertz. We won't be able to see anything on the LEDs, right? So then, for that purpose, we are just using this button. So by pressing this button, we are just simulating the passage of the clock. So when you press this button, so if the button is not pressed, it's 0. But when you press this button, it momentarily goes to 1, and as long as you press it, it is stays at 1. Okay, so that's how we are simulating the clock here. Okay, so now I mean we can do everything in the software, and then as I said, if you wanted to really check your design whether really it's working in the hardware, so we need to really do this Vivado flow, and then use these switches and LEDs to really check your design. That's what we did it, and believe me, so even like last year we had one course on advanced digital design. Even some of our students did a kind of a processor. It's a kind of a MIPS processor, and then even to test that also they will use the same approach. But of course here, I mean in a bigger design you will need a lot of inputs, right? Okay, so it's maybe inputs might be more than 16 or whatever. Instead what they did was, so they wrote some kind of a small program to really have some kind of a Fibonacci series which get displayed here. Okay, they wrote a kind of a program for the processor in which they will generate a Fibonacci series, and then the Fibonacci series they will display here. So the moment you release the reset button, the program will running. So the program will really show the Fibonacci series numbers 0 0, right, 0 1 1, and 1 plus 1 2, 2 plus 1 3, 3 plus 2 5. The Fibonacci series up to 999 they're showing here. Okay, I mean that's one way of let's say kind of using this board as well. So not only for the small designs, even to a bigger design up to some extent we can use it. But as I said, that bigger design, if you want to really test it, I mean we might need more than 16 inputs, so we do not have. So we can write some programs which does actually the functionality and check it. For instance, if you wanted to really control a stepper motor, so we can connect something here. Maybe again maybe you're not seeing the board, so we can come and connect something to this PMODs here, the PMODs here. Okay, the PMODs here you can connect it, and you can really connect some in a real time kind of some data boards. That way also we can do it. Okay, in this way this board is some kind of a versatile, and it's more of a laboratory purpose. Okay, so I think what I wanted to teach for today, I think I'm done. Okay, I think it was a bit lengthy, but it's fine. So from the next lab onwards, I think it should be much more simple. Okay, so what you do is maybe I'll try to send out an email with like what you need to do it, and a small some kind of a assignment kind of a thing, that I might be asking some questions about related to reset and synchronous, asynchronous reset, and some other questions. You need to answer them. And as I said, so should I share the codes? Hello, should I share the codes or not?
Share the codes, sir.
Okay, I
Yes.
mean, so I mean, see, of course, I don't mind sharing the codes, of course. So, but you should really understand what is happening in the code, right? I mean, once you have these codes, right, maybe you just simply do iverilog and then then generate the VCD file and just see it. But I wanted to really to understand what is really written in the codes, like I explained for the D flip flop, right? So maybe you should also try to understand at your level that what is there in the T flip flop code, and then maybe T flip flop in the test bench, and whatever the the signals which are coming out of your iverilog simulation, and when you see in the GTK wave whether the signals make sense or not, that and all you should really have a look. Okay, so for the Vivado part, I don't expect that you should do the Vivado part, because maybe you don't have access to the tool and even the board. But I expect either you can download the model sim part or the iverilog part, and then simulate that the things which I gave. Okay, and then maybe you should submit your let's say the code as well as your waveforms and everything. Okay, so at least you try to change the test bench and try to generate a different signals and I mean submit, right? Otherwise you just simply maybe run my code and you'll get exactly the same thing, and all the reports of everyone looks the same. So I don't want to really see that. Okay, am I clear?
Yes, sir. So what is the deadline for this?
I mean, you tell me, so what is the deadline I should keep? But my intention is that we'll have maybe 2 more sessions. I think today it was a bit long, but for the rest of the sessions I'm sure that I'll be kind of very fast. Okay, so I think this, as I said, I think I wanted to do it bit long, this one, and then we have this experiment 9 and experiment 10. Okay, and then the biggest thing is your what to say your the term project. Okay, so the turn project will be evaluated much more seriously. Okay, and of course, as I said, if you are done with your turn project, okay, let me know. Okay, so what I can do is maybe I'll try to assign one student where you will get maybe some kind of a TeamViewer connection or something like that, hmm, where you will have access to the tool as well as this basis 3 board. Okay, I mean, maybe physically maybe we'll try to connect something like this. So then maybe with together with that student you are really doing your design and checking your design in the real FPGA board. Or maybe if you think that you are done, at least one of you, okay, I can take the design, and as I said, we need to little modify that code a little bit. Okay, and then before porting it, I can do it, let's say for one of you, and should, I mean, I can also explain what are the changes, and then I can really show it on one basis 3, that I can do it. But from my side, I planned maybe next lab experiment 9 and experiment 10, and then after that, I mean, we are done. But once you have your, let's say, this turn project one, at least one of you, if you have completed, then we can have just one more half an hour or 1 hour session, and then we are done for the labs. Is it clear?
Yes, sir.
Okay, so then it's already too late, so we can close now. Okay, so if you have any questions, just feel free to send me a mail or something like that. Okay, so I'll revert back to you with some kind of a report, or what should you should have in the report, and some questions. Okay,
Okay, sir.
okay, so